Hello, and welcome back to Sleep Gravity. Rock often gives us the impression of something permanent, something that barely changes at all. It lies beneath our roads, rises into mountains, preserves traces of ancient oceans, and endures far longer than any human lifetime. But that solidity exists only within a relatively narrow range of temperatures. When rock is heated intensely enough, for long enough, its rigid structure begins to break down. Minerals are no longer held in fixed positions, and the material that once formed solid ground gradually becomes a dense liquid, glowing with its own internal heat. On Earth, molten rock usually appears only in small regions around volcanoes. Lava flows down their slopes, cools in the air, and hardens into new crust. Most of the planet remains covered by solid ground and liquid water because surface temperatures are not high enough to transform the entire upper layer of rock into an ocean. On worlds orbiting extremely close to their stars, that familiar balance may disappear. Heat does not merely melt a few streams of stone. It can sustain regions of magma so vast that even the horizon no longer leads towards solid land. TOI 561b may be one of those worlds. It is a super-Earth, larger and more massive than our own planet, orbiting an ancient star at such close range that each year lasts only a little more than 10 hours. Between morning and evening on Earth, it could complete nearly 2 full orbits around its star. One hemisphere is likely locked toward the source of light, receiving uninterrupted heat through millions, and then billions, of these brief revolutions. At such a distance, the dayside surface is hot enough to melt many kinds of silicate rock. Separate regions of magma may merge into a vast ocean that continuously absorbs energy from the star. Above it, material rising from the molten surface may form mineral vapor, while deeper layers continue to move through convection. This is not an ocean of water, blue waves, or familiar coastlines. It is a heavy, luminous, slowly moving surface, where the material that forms mountains on Earth exists as a liquid. A small planet that remains close to its star for a long time would normally be expected to lose most of its atmosphere. High-energy radiation heats the upper layers of gas, causing some particles to move fast enough to escape the planet's gravity. Streams of charged particles from the star also continually strike the atmosphere's outermost regions. Over billions of years, these processes could leave behind an almost bare world, with little more than a scorching rocky surface and a very thin layer of mineral vapor. TOI 561b appears to have had more than enough time to reach that state. Its star belongs to an ancient population within the Milky Way, suggesting that the planetary system may have existed for roughly 10 billion years. If the planet was once surrounded by an early atmosphere, that gas would have endured intense light and radiation for a span of time nearly twice the sun's current age. A thick sky above the magma ocean is therefore not what the simplest models would naturally predict. Observations from the James Webb Space Telescope have changed that picture. Webb does not see TOI 561b as a clearly resolved sphere, nor has it photographed clouds or streams of magma across the surface. The planet is too distant, and its light is far too faint compared with the nearby star. Instead, the telescope can track extremely subtle changes in the infrared light coming from the entire system, especially when the planet passes behind the star and the heat it emits briefly disappears from view. From that tiny difference, scientists can estimate the brightness temperature of the planet's dayside. The result still reveals an extraordinarily hot world, but not one as hot as a bare rocky surface should be. A model with no atmosphere predicts a temperature close to 2,700 degrees Celsius, while Webb measured a value of about 1,800 degrees Celsius. A gap of nearly 900 degrees is far too large to be treated as a minor measurement error. Some of the heat may be carried away from the dayside before it escapes into space. A thick atmosphere could absorb radiation from the magma surface, transport energy toward the night side, and make the layers observed by Webb cooler than the molten rock deeper below. If mineral clouds are present, they may also reflect part of the incoming starlight, reducing the amount of energy that reaches the magma ocean. The current data cannot yet reveal the exact composition of this atmosphere, but a completely airless world is becoming increasingly difficult to reconcile with what the telescope has recorded. The source that sustains the atmosphere may lie within the sea of molten rock itself. Magma can contain dissolved water, carbon dioxide, and many other volatile substances. As temperature, pressure, or internal motion changes, these materials can escape from the liquid and become gas. Part of the atmosphere may still be stripped away by the star, while fresh material is continuously supplied by the ocean below. Gas may also dissolve back into the magma, creating a long-lasting cycle of exchange between the planet's interior and its sky. Above that ocean, the space may not be clear or transparent. Starlight could be dimmed by heat haze and suspended mineral particles. Material carried by winds toward cooler regions may condense into silicate clouds, then fall as tiny grains of rock before evaporating once again. This remains a picture constructed from models, rather than weather observed directly, but it reveals how complex the sky of a lava planet might become. TOI 561b, then, may be more than a sea of fire orbiting close to its star. It could be a system in which matter is constantly exchanged among molten rock, atmosphere, and space. Its sky may exist, not because it was never lost, but because the magma ocean has quietly continued to replace the material escaping from the planet over billions of years. To understand this unusual balance, we must first move closer to the orbit of TOI 561b, where a year ends after little more than 10 hours, and starlight never leaves the dayside hemisphere. On Earth, a year is long enough for the light to change through several seasons, for trees to pass from new buds to falling leaves, and for a person to nearly forget how the first day felt by the time the final weeks arrive. On the world orbiting extremely close to the star TOI 561, that entire span has been compressed into a little more than 10 hours. One orbit begins and ends, and the next is already underway before a clock on Earth can complete half a day. That brevity does not mean time itself passes more quickly. Every process on the planet still unfolds according to its normal physical rhythm. Rock still needs to absorb enough heat before it melts. Gas still moves in response to pressure differences, and light still crosses space at the same speed. Only the path around the star has become very small, turning each year from a long cycle into a steady recurring beat, repeated without pause throughout a history spanning billions of years. This world orbits so close to its star that, if placed in our solar system, it would lie deep within the space between the Sun and Mercury. There, strong gravity keeps the planet moving at high speed, while the short circumference of its orbit allows each revolution to end quickly. There is no pause at the close of a year, and no true boundary marking the beginning of the next. The motion simply continues, smooth and unbroken, like water circling endlessly around a basin without ever reaching a final point. A single Earth day is long enough for this world to experience more than 2 years. During one of our weeks, it completes nearly 16 orbits around its star, and within a month, that number rises into the dozens. Once the timescale stretches across millions or billions of years, counting individual revolutions no longer makes the picture easier to imagine. What remains more tangible is the persistence of the same conditions, the same extremely close distance, the same intense source of light, and the same continuous flow of energy pouring onto the surface. Gravity at this orbit does more than guide the planet around its star. It also influences the shape and rotation of the entire world. The side closer to the star is pulled slightly more strongly than the side facing away, creating a small deformation within the rock. Although this difference is not enough to tear the planet apart, it repeats across countless orbits, gradually draining away any unsynchronized motion and bringing the planet's rotation rate closer to its orbital rate. The likely result is tidal locking, a state in which one hemisphere remains almost permanently turned toward the light while the other faces away. The planet still rotates, but it completes exactly one turn during each orbit. The two motions align so closely that, From the surface, the star would not appear to cross the sky as the sun does on Earth. Instead, it would remain in nearly the same position year after year. In the region facing directly toward the star, light always shines down from above. There is no afternoon when the source of heat slowly sinks toward the horizon, and no night when the rock can release the energy it has stored. The surface receives radiation continuously, growing hotter until many minerals can no longer remain solid. If a vast layer of magma exists there, it is not the result of a brief eruption, but a state that may be sustained over long periods by light that never disappears. Farther from the hottest point, the star gradually hangs lower in the sky. Its energy is no longer concentrated over a small area but spread across a broader surface, causing temperatures to decline. The transition may unfold across a wide region where molten rock, partially melted material, and newly solidified crust continually replace one another. This may not be a sharply defined shoreline separating a magma ocean from solid ground, but rather a shifting boundary shaped by heat flowing below and gases moving above. Beyond that lies the hemisphere that receives no direct light. Without an atmosphere thick enough to transport heat, the dark side would cool more rapidly, allowing magma to solidify and form a rigid crust. One half of the planet would remain under constant stellar heating, while the other stayed in lasting darkness. These two regions would not alternate between day and night as they do on Earth, but would exist beside one another through every orbit. Between them lies a band of nearly permanent twilight. The star neither rises nor sets there, but remains low along the horizon in an unending glow. If the atmosphere is truly dense, its light must travel through a longer stretch of gas before reaching the surface, leaving the transition zone hazy with heat and suspended mineral particles. Ahead lies a sea of molten rock beneath intense light. Behind it is a dark region where the surface may cool and harden. Between them, both states may meet in a place that is never fully day and never entirely night. Tidal locking can make such a world seem divided into two absolute halves, but matter rarely follows boundaries that simple. Heat can travel through deep layers of rock, magma can circulate beneath the surface, and the atmosphere can move from the hot side toward the cold. If the winds are strong enough and the gaseous layer thick enough, the energy received on the day side will not remain there completely. Some of it may be carried beyond the horizon, reducing the temperature difference between the two hemispheres and changing the size of the molten region. This becomes especially important when considering the Webb data. The hemisphere facing the star does not emit as much heat as a bare surface should. Some of that energy appears to have been reflected, absorbed, or transported elsewhere before escaping into space. The short orbit and the tidally locked state therefore do more than create the setting for an intensely hot world. They also shape every motion within the atmosphere that may surround it. If an atmosphere exists on the day side, it would be heated until it expands. The contrast with the dark hemisphere would create planet-wide currents, carrying gas across the twilight zone and onward into the night side. There, the air would cool, grow denser, and perhaps return through lower layers. Rather than a motionless sky above the magma ocean, the planet may be wrapped in a continuous system of circulation, driven by the contrast between eternal light and eternal darkness. That rhythm may have persisted for an immense span of time. The host star belongs to an ancient population of the Milky Way, and this planetary system may have formed around 10 billion years ago. The extreme heat of the present, then, is not necessarily a brief phase that began only recently. The same hemisphere may have faced the star through most of the system's history, while its little more than 10-hour orbits repeated so many times that the surface, interior, and atmosphere all had time to settle into their own form of balance. This is what separates the world from the image of a planet being destroyed in a single violent moment. It is not falling into its star, nor does it disappear after only a few revolutions. An extremely close orbit can remain stable for a very long time, as long as the planet's speed and distance remain balanced against gravity. The tremendous heat is not a sudden event, but a background condition that has shaped every layer of matter for billions of years. Over that time, the upper rock may have melted, cooled, and then melted again in different regions. Gas may have escaped from the surface, been lost to space, or dissolved back into the magma. Lighter substances would have escaped more easily, while heavier components remained behind. The entire planet has been restructured by its short orbital rhythm, not through one single transformation, but through the almost endless repetition of the same source of heat and the same gravitational pull. A year lasting only a little more than 10 hours is therefore more than an astonishing number. It helps explain how starlight can sustain a sea of molten rock, why the two hemispheres may have such different conditions, and why any surviving atmosphere must move through an environment without day and night in the familiar sense. The orbit is the framework that holds the entire world in this state, while everything happening at the surface is part of matter's long response to a source of energy that never turns away. Beneath the fixed light of the star, rock is no longer a quiet foundation. It softens, flows together, and begins to move like a liquid, forming an ocean without water that may stretch across much of the dayside hemisphere. To understand how the atmosphere above it might be sustained, we must first descend closer to that surface, where familiar minerals have crossed the boundary between solid ground and a molten sea. The rock beneath our feet seems to belong to the quietest part of a planet. It bears the weight of oceans, supports continents, and changes so slowly that most of its motion can be recognized only across thousands or millions of years. That sense of permanence makes a solid surface seem like the natural state of every rocky world. In reality, it is only the state matter can maintain while temperature and pressure remain within a certain range. Beyond those limits, the ground can soften, crystals begin to lose their structure, and entire layers of rock can become a glowing, molten liquid. There is no single temperature at which every kind of rock melts at once. Rock is made of many different minerals, each with its own melting point and its own response to pressure. As temperatures rise, some minerals become liquid before others, slipping between the portions that remain solid and turning the surface into a thick mixture, like rock caught midway through melting. Only as the heat continues to increase does the proportion of liquid become large enough that the solid framework can no longer preserve its original shape. On Earth, this process usually takes place deep beneath the crust, where magma forms through the partial melting of rock in the mantle. When that material rises and reaches the surface, it is called lava. The distinction between the two terms is mainly a matter of location. Magma remains underground, while lava has emerged into the open. On a world with a vast molten surface, that boundary becomes less clear because the liquid layer may be both part of the planet's deeper interior and the surface directly exposed to the atmosphere. The hemisphere of TOI 561b that always faces its star receives enough energy for many kinds of silicate rock to cross their melting point. Silicates are the widespread family of minerals that make up most of the crust and mantle of rocky planets, including Earth. Materials that form mountains, basalt, and the deeper layers beneath continents may exist there as a molten mixture rich in magnesium, silicon, oxygen, iron, and many other elements. If the ocean on that world truly covers a large part of the surface, it is not made from a single uniform substance, but from a complex chemical sea whose composition changes with temperature, depth, and the volatility of each element. The phrase, magma ocean, often brings to mind a bright red sea, churning violently beneath a dark sky. The real scene may be much quieter, heavier, and far more difficult to see through. Molten rock is denser than water, and its viscosity depends strongly on both temperature and composition. The hottest regions may flow relatively easily, while cooler areas become thicker, move more slowly, and may form temporary solid films across the surface. These layers could crack, sink, or be pulled apart as hotter material continues to rise from below. The glow of the molten sea would not necessarily be only red. Hot matter emits light according to its temperature. At lower temperatures, the surface may appear deep red. As the heat increases, the glow gradually shifts toward orange, yellow, and nearly white in the hottest regions. A thick atmosphere, however, could absorb and reshape much of that radiation before it escapes into space. Even from above the clouds, the magma ocean might not appear as a clearly shining expanse. It may be visible only through dim openings in the atmosphere, like a hidden source of light beneath a hot haze filled with mineral vapor. Below the surface, heat drives convection. Hotter material usually expands, becomes less dense, and rises, while cooler material tends to sink. This continuous exchange distributes energy throughout the magma layer, making the ocean not a motionless body of liquid, but a system moving on a planetary scale. These convective currents may flow far more slowly than waves across an ocean of water. Yet the amount of material involved is enormous, enough to carry heat and chemical compounds from deep layers toward the surface. Because the orbit is tidally locked, energy from the star remains concentrated on the same hemisphere, creating an uneven pattern across the ocean. Near the point that always faces the star directly, the surface receives the greatest amount of energy and may remain molten to a greater depth. Toward the twilight region, temperatures gradually fall, the magma grows thicker, and the proportion of solid rock increases. If the night side is cold enough, its surface may freeze into a thick crust, leaving the sea of rock confined mostly to the illuminated hemisphere and narrowing as it approaches the horizon. This was once the relatively simple picture imagined for tidally locked lava planets: a hot ocean on the day side, frozen rock on the night side, and a transition zone between them. New data suggests that this boundary may need to be reconsidered. If the atmosphere is truly dense enough to carry a significant amount of heat toward the dark hemisphere, the molten area would be larger than bare rock models predict. Under the right conditions, heat from the atmosphere and currents within the magma below might even prevent most of the surface from freezing completely, raising the possibility of an ocean that extends across nearly the entire planet. That possibility has not been observed directly. Webb cannot see through each layer of gas and precisely map where the rock is liquid or solid. The depth of the magma, the extent of the molten surface, and the condition of the night side still depend on information that has not yet been determined, especially the atmosphere's composition and pressure. A global magma ocean should therefore be understood as a model that may fit certain conditions, rather than a confirmed image of the entire planet. Even if it is limited to the day side, the molten layer could still reach a scale unlike anything produced by volcanism on Earth. The largest lava lakes here cover only a tiny fraction of the surface. They are usually fed by magma systems deep below and may change over months or years. On that world close to its star, the energy does not come mainly from a local magma chamber. It shines down continuously from outside, affecting an area the size of a continent or even an entire hemisphere. The ocean does not need a volcanic crater in order to exist, because the surface of the planet itself has become the molten region. This also changes what volcanism means. On Earth, an eruption carries material from the interior through the solid crust and releases it at the surface. If most of the dayside crust has already melted, magma no longer has to find narrow fractures in order to rise. Deep material may mix directly into the ocean above, bringing heat and compounds that were once held under high pressure. The release of gas would not necessarily occur through separate eruption columns, but could spread across the surface, like an immense ocean slowly breathing into the atmosphere. Within molten rock, substances such as water and carbon dioxide can remain dissolved, even though the surface is far too hot for liquid water to exist. In this case, water does not take the form of droplets or blue oceans. Its molecules may remain within the magma, escape as vapor, or be broken apart by the high-energy environment of the upper atmosphere. Other volatile substances may also take part in this process, creating an atmosphere with a composition very different from the thin layer of rock vapor produced by a simple bare surface. Rock itself can also evaporate when temperatures become high enough. Sodium and some other volatile elements leave the magma first, while less volatile components require greater heat before entering the atmosphere. Over time, this selective evaporation could alter the composition of the uppermost layer, gradually depleting it of elements that escape easily and enriching it in heat-resistant minerals. Convection from below, however, may continue to carry fresh material upward, preventing the surface from ever reaching a completely fixed state. In cooler regions, mineral vapor may condense. Atoms and molecules that once escaped from the magma can come together again as tiny particles, forming silicate clouds or falling back toward the surface. The cycle resembles the movement of water on Earth, but instead of oceans evaporating into clouds and returning as rain, the circulating material may consist of the very substances that form rock. A mineral particle created in a cooler part of the atmosphere might begin to fall, grow steadily hotter, and evaporate again before ever reaching the ocean below. Every part of the system affects the others. Heat from the star determines how much rock melts and how quickly it evaporates. The composition of the magma influences which gases are released. The atmosphere, in turn, controls how energy escapes, how much heat is carried toward the night side, and how far the molten sea extends. If the atmosphere grows thicker, it may expand the melted region. As the ocean spreads, the area releasing gas also increases, adding still more material to the sky. This connection means the surface is no longer simply the layer beneath the atmosphere. The magma ocean may act as an immense reservoir, storing volatile substances and releasing them over long periods. At the same time, it may also absorb some of the gas again, depending on pressure and chemical composition. The sky and the molten sea, therefore, do not exist as two separate layers, but as two states within a single system that is constantly exchanging matter. From such a great distance, Webb cannot reveal convective currents, temporary plates of crust, or changing patterns of light across the magma surface. What the telescope records is only the faint amount of heat escaping from the entire dayside hemisphere. Even so, that signal carries the influence of every layer below: the temperature of the rock, the depth of the ocean, the composition of the gas, and the possibility that clouds are reflecting starlight. A measurement that seems to describe only temperature opens a view onto an entire surface in constant transformation. Rock on this world is no longer where all motion comes to an end. It rises from deeper layers, cools near the surface, releases gas, and may then sink again to begin another cycle. At the top are the most changeable mineral layers, sometimes existing as glowing liquid, sometimes escaping into the atmosphere, condensing into particles, and returning to the sea. The magma ocean does not merely lie beneath an unfamiliar sky. It may be the source of matter that allows that sky to continue existing. The part of the molten sea that always faces the star receives heat without pause, but that energy does not remain entirely where it arrives. Some is carried deeper into the magma, some escapes as radiation, and some may be transported beyond the horizon by the atmosphere. The division between day and night therefore does more than determine where rock remains molten. It also creates the driving force behind atmospheric currents that may circle the entire planet. On Earth, light always carries a sense of time. The sun, climbing higher, tells us that morning is passing. Tree shadows grow shorter at midday and lengthen again as evening approaches, and the disappearance of daylight opens a period of darkness in which the surface can gradually cool. This rhythm is so familiar that day and night seem inseparable from the nature of any world. But on the planet orbiting extremely close to the star TOI 561, light may not move across the sky in the same way. With one hemisphere almost always facing its star, the source of light changes position so little that time is no longer marked by sunrise or sunset. It simply continues beneath a sky that remains nearly unchanged through countless orbits. Near the point facing the star most directly, light falls almost straight down. If thick clouds do not hide it, the star would stand high in the sky and barely move from that position, even as the planet completed another year in little more than 10 hours. Energy continues to pour onto the same region of the surface, uninterrupted by darkness and without waiting for a new cycle to return. The rock there has no long period of rest in which to release the heat it has stored. Whatever energy escapes into space is continually replaced by incoming starlight, sustaining a broad hot region around the center of the dayside hemisphere. The idea of day on this world therefore does not refer entirely to time. It describes a place. Conditions of light would change as one moved across the surface, while any fixed location could remain forever within the same part of the cycle. Near the center of the illuminated hemisphere lies a region of eternal noon. Farther away, starlight arrives at a slant, like an afternoon that never ends. At the boundary with the dark side, the star rests close to the horizon without ever truly setting. Instead of day following night, different states of light are spread beside one another across the planet, each region maintaining its own climate for immense spans of time. This division would not form perfect circles clearly drawn across the surface. Heat does not stop exactly where the light begins to weaken, and matter does not respond instantly as it passes from one region into another. Hot rock may continue flowing toward cooler areas before solidifying. An atmosphere, if thick enough, would carry energy beyond the horizon. Deeper layers of magma could also distribute heat beneath the crust, shifting the boundary between molten and solid rock according to convective currents. The real picture would therefore resemble a broad transition zone, where several states of matter coexist, rather than one glowing red half placed beside another that is completely frozen. At the hottest point, the amount of incoming energy may keep the surface far above the melting temperatures of many silicate minerals. The magma ocean there could be deeper and less frequently interrupted by temporary plates of crust. Moving outward, the light reaches the ground at an increasingly shallow angle, spreading the same radiation across a larger area. Temperatures gradually fall, the liquid grows more viscous, and the most heat-resistant minerals begin to crystallize first. Depending on their density and composition, these newly formed crystals may float near the surface, sink deeper, or be swept back toward hotter regions by currents within the magma. This change occurs gradually across distance, yet its total scale may be enormous. An imagined journey from the center of the dayside toward the twilight zone would pass not only through different levels of light, but through many states of rock. A white-hot or pale yellow surface beneath the strongest radiation might slowly shift toward orange, deep red, and then darker tones as the material cooled. Continuously molten regions could give way to thick, crystal-rich magma, followed by solid plates fractured by heat rising from below. There would be no coastline in the familiar sense, because the boundary between the sea of rock and solid ground might be continually stretched, broken apart, and rebuilt. The atmosphere would make this entire pattern more complex. If the layer of gas were extremely thin, radiation from the surface would escape relatively directly, allowing the dayside to lose heat into space even as the star continued heating it from above. Temperatures would then be controlled mainly by the angle of incoming light and the rock's ability to absorb it. A thick atmosphere, however, could stand between the surface and space, absorbing infrared radiation from the magma and emitting it again in many directions. Some of that energy would return downward, some would escape, and some would be carried by moving air toward regions, receiving no direct starlight. The air above the hottest region would expand as it absorbed heat, changing in pressure and density with altitude. From there, gas would tend to move toward cooler areas, creating winds that stretch from the dayside toward the night. Because the planet rotates in step with its orbit, the motion of the atmosphere would also be deflected by rotation, possibly forming broad currents that circle the world rather than following the shortest path from hot to cold. Their true structure would still depend on the atmosphere's unknown thickness, composition, and pressure. But any gaseous layer strong enough to transport heat would be unlikely to remain motionless above the surface. In the lower atmosphere, winds may sweep across the magma ocean, collecting mineral vapor and compounds released from the molten rock. As the gas moves into cooler regions, its ability to hold those substances decreases. Some of the material may condense into tiny particles, making the sky more opaque and forming layers of mineral clouds. These particles could reflect part of the starlight while also absorbing heat from below, meaning that the climate of the dayside would be controlled not only by its distance from the star, but also by the way clouds form, drift, and disappear. The sky above the region of eternal noon may therefore be nothing like a clear day on Earth. If the atmosphere is rich in mineral vapor and suspended particles, the disk of the star could appear blurred behind a white glow or a yellowish haze. Light would scatter across the sky, giving the horizon colors determined by the substances floating in the air rather than the familiar blue of Earth. The magma below might not appear as a clearly visible Red Sea either, because many wavelengths emitted by the surface could be absorbed by the atmosphere before traveling far. At higher altitudes, where pressure is lower and gas loses heat more easily to space, minerals may condense in different ways. Clouds formed there would not need to resemble the soft white shapes seen on Earth. They might consist of wide layers of extremely fine particles, covering much of a hemisphere, or gathering into bands along atmospheric currents. If the clouds reflect starlight efficiently, the surface below would receive less energy. If they strongly absorb infrared radiation, they would instead trap heat in the lower atmosphere. The same material could make the planet appear brighter in reflected starlight, while also slowing the escape of heat. This means that the dayside is not necessarily a bare surface exposed directly to the star. Between the star and the magma sea may lie a thick, dynamic atmospheric system that continually changes the way energy enters and leaves. Stellar radiation must pass through clouds and vapor before reaching the rock. Heat emitted by the magma must then travel back through those same layers before escaping into space. Every act of absorption, reflection, and emission can make the temperature measured from a distance different from the true temperature of the surface hidden far below. Near the twilight region, starlight travels through a longer path within the atmosphere. Even a layer of gas that is not especially thick becomes harder to see through when viewed at a shallow angle near the horizon. If mineral clouds exist, this area may be covered by a long band of glowing haze, with the red or white-hot disk of the star hanging low above partially molten rock. Temperatures may fall enough for some compounds to begin condensing, making the transition zone a region of more active mineral weather, where particles form in the air before being carried farther toward the dark side. There is no sunset in the sense of light gradually disappearing as the planet turns away. The glow remains almost fixed, while matter continues to move through it. Winds from the dayside carry heat and mineral vapor, cloud particles drift toward the night, and cooler currents may return at different altitudes. The zone of eternal twilight is not a motionless region, but a place where two climates meet and continually exchange energy. Beyond the horizon, direct starlight no longer reaches the surface, but darkness does not necessarily mean complete cold. Gas arriving from the dayside may still carry heat, while deeper rock continues to release energy stored within the planet's interior. If that transport is efficient enough, the night side could remain far warmer than predicted for an airless body of stone. The surface may still solidify, but the crust could be thinner, heated from below, or continually covered by material condensing out of the sky. The difference between the two hemispheres is one of the keys to understanding the layer of gas surrounding the planet. A bare, rocky world usually retains most of its energy where the light falls, creating an extremely hot dayside and a much colder nightside. The thicker the atmosphere and the stronger the winds, the more widely heat can be distributed, cooling the illuminated hemisphere while warming the dark side. Webb has so far measured mainly the radiation coming from the dayside, but its lower than expected temperature already suggests that the energy is no longer remaining where it is first absorbed. This redistribution does not need to make the surface mild. Even after some of the heat is carried away, the region of eternal noon would still be hot enough for rock to remain molten. What changes is not the extreme nature of the world, but the way its energy is arranged. Instead of one bright region holding nearly all the heat beneath an almost empty sky, there may be a connected system in which magma warms the atmosphere, gases move beyond the horizon, clouds reflect starlight, and material condenses in more distant regions. Over billions of years, these movements may have settled into a relatively stable state. Not stable in the sense that everything has stopped, but in the sense that continuous change has reached a balanced rhythm. Energy enters, is redistributed, and then escapes. Rock evaporates, condenses, and returns to the surface. Gas is gradually lost to space, but is also replenished by the magma. Beneath a star that never sets, endurance may come not from stillness, but from the continued repetition of these cycles. Before the new data arrived, many simple models left out most of these complex layers. A rocky planet, orbiting so close to its star, after enduring roughly 10 billion years of intense radiation, seemed likely to have lost all of its lighter gases and been left with little more than a hot surface and a thin layer of rock vapor. That picture made sense. If the star was always removing material faster than the interior could replace it. But the day side, observed by Webb, does not glow like a bare surface, and the older picture has begun to reveal a gap that is increasingly difficult to ignore. Before the new measurements appeared, the simplest picture of a rocky planet orbiting far too close to its star did not contain many layers to explore. Extreme heat melted the surface, intense radiation eroded the atmosphere, and billions of years completed the rest of the process. In the end, such a world was expected to be little more than a layer of scorching rock, perhaps covered by magma on the day side, and a small amount of mineral vapor rising above it. There would be no ocean of water, no thick primordial atmosphere, and little light material left to create a complex sky. That expectation was not based on arbitrary imagination. It grew from what scientists already understood about how planets form and how they change after their birth. During the early life of a star system, conditions are often more violent than they are today. A young star rotates rapidly, remains highly active, and releases large amounts of high-energy radiation. Ultraviolet light and X-rays do more than illuminate the upper atmosphere. They transfer energy into gas molecules, heating the outermost layers and causing them to expand. When gas at high altitudes becomes hot enough, its particles move more rapidly. Some of the lighter particles may reach speeds that allow them to overcome gravity and escape the planet. This process is not like an outer shell being stripped away all at once. It happens gradually, molecule by molecule, as particles leave the highest layers and gas from below continues, rising to replace them. If material escapes faster than it can be replenished, the atmosphere slowly grows thinner over millions and then billions of years. Hydrogen is often among the easiest elements to lose because its atoms are extremely light. A young planet may once have retained a significant amount of hydrogen from the cloud of gas in which it formed. But close to a star, this layer can easily be heated and expanded. Escaping hydrogen may also carry other elements with it, like a powerful current sweeping additional material away from the planet. This early period may remove most of the primordial atmosphere before the surface, and interior have time to settle into a stable state. Distance from the star makes this process more intense. Around the same star, a nearby planet receives far more energy than one orbiting farther away. High-energy radiation is concentrated in the upper atmosphere, while the heat from ordinary starlight continues warming the surface below. Expanded layers of gas may reach farther from the planet, into regions where gravity becomes weaker and matter is more easily disturbed by streams of particles from the star. That stream of particles is commonly called the stellar wind. It is not wind in the familiar sense of air moving across Earth, but a flow of electrically charged particles released by the star and carried throughout the entire system. When these particles encounter a planet's atmosphere, they can transfer energy, ionize matter, and help drive some of the gas into space. The extent of this effect also depends on the planet's magnetic field, the composition of its atmosphere, and the structure of its upper layers. But for a world orbiting extremely close to its star, the accumulated influence over time is difficult to ignore. The planet's gravity pulls in the opposite direction. A more massive world can hold matter more effectively than a smaller body because gas must reach a greater speed to escape. This is why giant gaseous planets can preserve thick layers of hydrogen and helium, while the Moon has almost no substantial atmosphere at all. The ancient super-Earth orbiting TOI 561 is more massive than our planet, so its gravity is strong enough to make atmospheric loss more difficult. Even so, powerful gravity does not automatically guarantee that an atmosphere will survive when temperatures are extreme and erosion continues for billions of years. The type of molecule also makes an important difference. Light gases reach escape speed more easily, while heavier molecules such as carbon dioxide and some oxygen-bearing compounds are more difficult to remove. A planet may lose hydrogen rapidly while retaining heavier gases, or its interior may create a second atmosphere through geological activity after the primordial one has disappeared. Atmospheric loss is therefore rarely a simple process in which every component vanishes at the same rate. On a cooler world, a solid crust may trap many volatile substances inside, releasing them only through isolated volcanic regions. Here, a molten surface creates a much broader pathway between the interior and the sky. Magma may continually release material, yet the intense heat also causes gas to expand and escape more easily. One process replenishes the atmosphere while the other erodes it, creating a long competition between what the planet brings upward from below and what the star removes from its highest layers. In the earliest simple models, atmospheric loss was usually expected to win. The star system has existed for roughly 10 billion years, long enough for even a relatively slow escape rate to produce an enormous result. If each orbit removed only a tiny amount of matter, the immense number of repeated cycles could still gradually drain the planet's reserves. Across such a timescale, a thick atmosphere seemed difficult to maintain without an extremely large source of replacement gas, or a mechanism that retained matter more efficiently than expected. The image of a bare rocky world therefore became a reasonable starting point. The dayside surface would be heated enough to create a sea of magma. Some of the more volatile components within the rock would leave the liquid and form a thin layer of vapor above it. Winds would carry that mineral vapor toward cooler regions, where it would condense and fall back to the surface. This entire cycle could occur without a thick atmosphere containing large amounts of water, carbon dioxide, or other volatile substances released from deep within the planet. Such a layer of rock vapor would be very different from the atmosphere familiar to us on Earth. The air around us consists mostly of nitrogen and oxygen, with enough pressure to transport heat, form water clouds, and sustain vast weather systems. Mineral vapor above a magma sea might be far thinner, concentrated near the hottest region, and quick to condense as it moved into colder areas. It would still be gas, but not necessarily dense enough to strongly conceal the surface or transport large amounts of heat to the night side. In this picture, the day side would have to release most of its energy close to where it was received. Starlight would descend, heat the rock, and then the surface would emit infrared radiation back into space. With only a thin layer of vapor, little energy would be stored in the atmosphere or carried around the planet. The temperature measured from a distance would therefore remain close to the level expected for a bare surface exposed to the same amount of starlight. This is where the models produced a clear prediction. By knowing the size and temperature of the star, the planet's orbital distance, and the amount of energy it receives, scientists could estimate the dayside temperature expected if the surface absorbed most of the incoming light and transferred almost no heat to the night side. The calculation did not require knowledge of every wave in the magma or every small cloud. It only needed to follow the overall balance between energy entering the planet and energy escaping from it. For a bare rocky world orbiting so close to its star, the result was a dayside temperature near 2,700 degrees Celsius. Under those conditions, the surface would not merely melt. Many of its components would also evaporate rapidly. The amount of infrared radiation escaping into space would have to be enormous, because hotter matter emits more energy. When the planet passed behind its star, the temporary disappearance of that heat should have produced a signal consistent with the predicted glowing surface. The bare rock model was appealing because it was simple and based on processes that were already relatively well understood. The extremely close orbit supplied the heat. The system's great age provided time for gases to escape. Stellar radiation removed light material. The magma surface produced the remaining layer of mineral vapor. Each part followed naturally from the one before it, without requiring an immense reservoir of gas to remain hidden within the interior. But a simple model is not necessarily a bad model. It is often where science begins, by removing layers that may not be necessary and asking whether the most basic factors are enough to explain the data. Only when observations fail to match the prediction must the missing layers return. The possibility of a thicker atmosphere, stronger heat transport, clouds that reflect starlight, or a magma ocean containing more volatile material than expected. Even the idea of a star stripping away an atmosphere must be viewed at a slower pace. There is no invisible hand pulling the entire sky away from the planet. Gas escapes through several different pathways, each depending on the altitude, temperature, electrical charge, and mass of the particles involved. Some molecules leave directly because they are moving too quickly, some are broken apart by radiation, and charged particles may be pushed outward by streams of matter from the star. Meanwhile, the lower atmospheric layers remain held by gravity and may continue to be replenished by magma. An atmosphere, then, does not necessarily move from full to empty along a straight path. Its composition may change. It can lose lighter substances while retaining heavier ones, grow thinner during the star's highly active youth, and then enter a slower stage as the star ages. The gas present today does not even need to be the same atmosphere that surrounded the planet when it first formed. It may be the product of a long history of renewal, released from the interior after the primordial atmosphere had already disappeared. None of this makes the expectation of a bare, rocky world unreasonable. Before measurements became sensitive enough, there was no way to know whether the supply of new gas could keep pace with the rate of atmospheric loss. By every familiar standard, a hot, ancient planet, orbiting extremely close to its star, remains a difficult place for an atmosphere to survive. The evidence would need to be strong enough to overturn the simple picture built from the planet's temperature, orbit, and the age of the system. This is where the James Webb Space Telescope enters the story. It does not need to see a thick layer of clouds directly in order to reveal that something is missing from the older model. It only needs to measure how much heat actually escapes from the day side and compare that value with what a bare surface should emit. When the observed amount is significantly lower, the gap between prediction and reality becomes evidence of layers of matter that cannot be seen with the eye. A bare, rocky body was once the most concise explanation, but that simplicity began to fracture as infrared light was measured with greater precision. Hidden within the faint signal of a distant planet, a thick atmosphere may be concealing the hottest parts of the magma sea, carrying heat beyond the horizon and preserving substances that billions of years should have removed. To recognize that invisible layer of gas, scientists first had to learn how to measure the light of a world that is always overwhelmed by the brighter star beside it. From our distance, this planet does not appear as a separate, visible sphere. Even to a large telescope in space, the light from the star overwhelms the faint heat emitted by the small world orbiting so close beside it. The apparent separation between the two objects in the sky is also too narrow for them to form two distinct points of light. For most of the observation, the telescope receives only a combined signal, in which the star's light and the planet's radiation blend together so completely that the smaller contribution nearly disappears. The difference can be imagined as a brightly lit room where a very hot object gives off a faint glow in front of a large lamp. While both are visible, almost everything the eye sees comes from the lamp. The smaller source has not truly vanished, but its contribution is too slight to notice easily. Only when the object is completely hidden does the total brightness of the room decrease by a tiny amount. If the measuring instrument is sensitive enough, that difference can reveal how much light the hidden object had been contributing. In the planetary system around TOI 561, a similar concealment happens at regular intervals. When the rocky world passes in front of its star from Earth's point of view, it blocks a very small fraction of the starlight. This event is called a transit, and it previously helped astronomers determine the planet's size. But when the planet continues through half of its orbit and passes behind the star, another part of the signal disappears. At that moment, both the reflected light and the thermal radiation emitted by the day side are temporarily prevented from reaching the telescope. The moment when the planet moves behind its star is known as a secondary eclipse. The name may sound technical, but the principle is fairly simple. Before the eclipse begins, the telescope receives the star's light together with the planet's much smaller contribution. While the rocky world is completely hidden behind the star, the telescope receives only the starlight. By subtracting one state from the other, scientists can recover the missing contribution, even though it makes up only a tiny fraction of the total signal. This measurement does not produce an image of the surface. It does not reveal streams of magma, clouds, or the boundary between day and night. What it records is the amount of energy escaping from the entire hemisphere facing the observer just before the planet disappears behind the star. Every hot and cool region on the day side, every layer of gas-absorbing radiation, and any clouds that may be reflecting starlight all contribute to that very small number. The James Webb Space Telescope monitored the system continuously for more than 37 hours. That is a relatively short time by the rhythm of human life, but long enough for the planet to complete nearly 4 orbits. Rather than observing only once and relying on a single signal, Webb recorded several repeating cycles in which the rocky world appeared, moved through its orbit, and passed behind the star in the same steady rhythm. Each repetition added more data, helping researchers separate the true planetary signal from small instrumental fluctuations or natural changes in the star. This repetition is especially important because the drop in light during a secondary eclipse is extremely small. From a single measurement, it would be difficult to know whether the change came from the planet, from a random fluctuation, or from noise introduced during the observation. When the same variation appears at exactly the expected time over several orbits, the case that it belongs to the hidden world becomes much stronger. The orbit of a little more than 10 hours, which creates such extreme conditions at the surface, also allows Webb to observe several eclipses within one relatively compact observing period. The telescope does more than measure the total amount of light. It also separates the signal into different wavelengths within the near-infrared range. Human eyes cannot see this kind of light, but hot matter releases a great deal of energy there. A stovetop that has just been turned off may no longer glow red, even though it still gives off heat that can be felt by the skin nearby. The magma ocean and the hot gas above it also emit radiation beyond the range of human vision, making infrared light a suitable way to search for the planet's thermal signature. Webb's NIRSPEC instrument recorded the signal between 3 and 5 microns. A micron is a unit used to measure the wavelength of light, equal to 1/1,000,000th of a meter. There is no need to remember the exact numbers to understand the meaning of the observation. What matters is that within this range of light, the heat from a world thousands of degrees hot can leave a measurable signal, while certain atmospheric molecules may absorb or emit radiation in different ways. If the planet were only a bare rocky surface, its thermal spectrum should resemble the radiation emitted directly by hot material. The amount of light at each wavelength would be determined mainly by the surface temperature and by how efficiently the rock absorbed or reflected energy. A very thin layer of mineral vapor might create a few small changes, but it would not be enough to conceal most of the heat from the ocean below. A thick atmosphere creates a different situation. Radiation from the magma must pass through many layers of gas before escaping into space. At some wavelengths, the atmosphere is relatively transparent, allowing Webb to see deeper and hotter layers. At others, atmospheric molecules absorb strongly, so the light reaching the telescope comes from higher regions where temperatures may be lower than at the surface. The observed spectrum therefore reveals not only how much energy the planet emits, but also carries clues about the depth from which that light is able to escape. This is somewhat like viewing a lamp through several layers of curtains. Where the fabric is thin, the light from the bulb remains clear. Where the material is thicker, the observer sees only a weaker glow filtered through the outer covering. Measuring only the total brightness may reveal that the source has been partially concealed. Separating the light by wavelength can also show that the covering does not affect every kind of light in the same way. Even so, the current data are not enough to identify every component of the atmosphere with certainty. Webb's measurements show that the emission spectrum does not match a bare rock model or a thin layer of mineral vapor particularly well, but several different gas mixtures can still produce similar results within the range observed so far. Water vapor, carbon dioxide, oxygen, and other chemical products have all been considered in the models, yet none can be claimed as a definite detection based on this observation alone. This is an important limitation because the phrase "atmosphere detected" can sometimes create the impression that the telescope has seen a complete layer of air and determined exactly what it contains. The reality is more cautious. Webb measured the amount of heat and the shape of the emission spectrum. When scientists attempted to reproduce those data using different models, scenarios with a thick atmosphere explained the results better than models of a bare surface. The presence of gas is therefore strongly supported, while its composition, pressure, and distribution around the planet remain uncertain. To turn tiny points of light on a detector into a meaningful temperature, researchers must also remove many other influences. The star is not a perfectly stable lamp. Its surface may fluctuate slightly, active regions can change in brightness, and the instrument itself undergoes very small variations as its temperature and viewing position shift. All of these effects must be modeled before the portion of the signal belonging to the planet can emerge. The analysis is therefore not simply a matter of taking two numbers and subtracting one from the other. The light is tracked over time, transits and eclipses are compared, unrelated variations are identified, and several physical models are tested against the corrected data. The final result still carries uncertainty, but the difference between the observed temperature and the prediction for bare rock is too large to be erased by minor adjustments alone. Here, absence becomes a source of information. While the planet remains beside the star, its heat is included in the total light received by Webb. When it disappears behind the star, a tiny amount of energy disappears with it. The telescope does not need to see the surface to know that the surface is radiating heat, nor does it need to photograph the sky to recognize that something is changing the way that heat escapes. Each eclipse lasts for only a small part of the orbit. During that interval, a world larger than Earth is completely hidden from view by its star. The dayside continues receiving heat, magma keeps moving, and the atmosphere continues carrying energy beyond the horizon. Yet not a single photon traveling directly from the planet reaches the telescope. That brief absence is precisely what allows its light, otherwise buried within the stellar signal, to be separated. This is one of the quiet paradoxes of modern astronomy. Scientists learn more about an object at the moment it can no longer be seen. A planet too small and too distant to form a clear image can still reveal its temperature, the structure of its atmosphere, and the way energy moves around it, all through the tiny change that occurs when it passes behind a star hundreds of light years away. From that signal, one striking number gradually emerged. The dayside has a brightness temperature of about 1,800 degrees Celsius, according to Webb's measurements. This is still hot enough to keep rock in a molten state, but it is significantly cooler than a completely bare surface should be. The difference of nearly 900 degrees does more than alter a calculation. It forces the entire picture of the planet to be rebuilt. The light that vanished behind the star left behind evidence of a layer of matter that cannot be seen directly. That atmosphere may be absorbing heat from the magma sea, reflecting part of the incoming starlight, and carrying energy toward the dark hemisphere. Before exploring how those atmospheric currents might move, it is worth pausing at the difference Webb has just measured, because this world remains hot enough for rock to flow, yet is also far cooler than earlier models had predicted. 1800 degrees Celsius is not a temperature that suggests anything gentle. At that heat, many kinds of rock have already lost their solid structure. Metals can melt, and the planet's surface is hot enough to emit much of its energy in the infrared. Viewed on its own, the number offers little reason to describe the dayside as cool. In astronomy, however, temperature becomes meaningful only when placed beside the conditions that produced it. A world orbiting extremely close to its star, receiving constant light on the same hemisphere and almost no darkness in which to cool, should be far hotter if its surface were completely bare. The predicted temperature of nearly 2,700 degrees Celsius was not chosen simply to make the scene seem more dramatic. It emerged from a relatively simple balance of energy. The star sends light toward the planet. Some may be reflected, while the rest is absorbed and must eventually return to space as thermal radiation. If the surface absorbs nearly all the incoming light, with no substantial atmosphere to transport heat and little energy carried to the night side, the day side must continue warming until the amount of heat it emits balances the energy it receives. Bare rock beneath uninterrupted starlight has few places to hide energy. A hotter surface radiates more strongly, much like a metal bar shifting from deep red to orange and then becoming brighter as it is heated further. Equilibrium is reached only when heat escapes quickly enough to balance the constant flow of energy from above. At this planet's extremely close orbit, that balance point in the simplest model lies nearly 900 degrees above Webb's measurement. That gap is far greater than a minor error or a difference caused by rounding. It is comparable to the difference between an environment already hot enough to melt rock and one so much hotter that many components of the magma evaporate rapidly. Both are extreme by earthly standards, but they produce very different surfaces, vapor layers, and rates of heat loss. A difference of this size suggests that the energy received from the star is not following the path predicted by the bare rock model. The value of 1, it is a brightness temperature, inferred from the amount of radiation the planet emits at the wavelengths observed by the telescope. In other words, scientists determine what temperature an ideal object would need in order to produce a similar amount of light, and then use that value to describe the signal. The distinction between brightness temperature and surface temperature becomes especially important when an atmosphere is present. On a bare world, most of the radiation travels directly from the hot rock, so the two values may be relatively close. With a thick layer of gas above the surface, light must pass through many layers of matter before escaping. Some wavelengths travel through easily and carry information from deeper regions, while others are absorbed so strongly that the telescope receives only radiation emitted by higher layers of the atmosphere. Those upper layers are often cooler than the magma surface below. If Webb is seeing mainly radiation from these regions, the planet will appear to have a lower brightness temperature than the true temperature of its molten ocean. The surface may still be significantly hotter, but its hottest regions are concealed by the atmosphere itself. This does not make the energy disappear. It only changes the place from which that energy is last emitted before leaving the planet. It can be compared to a room heated to an extreme temperature behind a thick door. Someone standing outside does not feel the full heat of the source inside, but mainly receives radiation from the surface of the door, which is cooler than the air beyond it. From the outside, the room seems less hot than it truly is, even though energy is still passing through several layers of material before slowly escaping. An atmosphere above the magma sea may play a similar role, but on a scale that covers an entire hemisphere. Atmospheric concealment is not the only way to reduce the heat observed by Webb. Some of the starlight may be reflected before it ever reaches the surface. Hot rock is generally dark and absorbs energy efficiently, but mineral particles suspended in the atmosphere could form brighter layers of cloud. If silicate clouds reflect a meaningful amount of incoming light, the magma ocean would receive less heat than predicted by a bare surface model. Its equilibrium temperature would then fall, even though the planet remained at the same distance from its star. The clouds would not need to reflect all the light to make a difference. A layer of particles covering much of the dayside could send a portion of the incoming energy back into space before it had time to heat the rock. This is somewhat like the difference between dark asphalt and a bright surface beneath the same sunlight. Dark material absorbs more energy and becomes hotter, while a lighter surface reflects part of the light. On a lava planet, clouds may perform that reflective role above the sea of molten rock. Energy transported to the dark hemisphere would also cause the dayside to emit less heat. As hot gas moves away from the region that always faces the star, it carries part of the energy absorbed from the surface. That heat no longer escapes immediately from the illuminated hemisphere, but travels through the twilight region and is emitted elsewhere. By measuring only the dayside shortly before the planet passes behind its star, Webb would see a cooler region than it would if all the energy remained in place. All three processes may be operating together. The atmosphere conceals the hot magma, clouds reflect some of the incoming starlight, and winds carry heat beyond the horizon. The current data do not allow scientists to completely separate the contribution of each mechanism. One model may require a thicker atmosphere with fewer clouds, while another may use highly reflective clouds combined with moderate heat transport. Several different arrangements can still produce radiation close to what Webb recorded. What the successful explanations have in common is that they all require more than a simple rocky surface. If the planet had only magma and an extremely thin layer of mineral vapor, heat from the dayside would still escape relatively directly. Rock vapor could absorb at certain wavelengths and produce small changes in the spectrum, but it would struggle to conceal enough energy to reduce the brightness temperature to the observed level. A thicker layer of matter, capable of storing and redistributing heat on a planetary scale, explains the gap more naturally. This does not mean that every atmospheric model will fit the data. The composition of the gas determines which wavelengths are absorbed, how the atmospheric layers are heated, and how efficiently energy is carried toward the night side. An atmosphere made mostly of mineral vapor would behave differently from one rich in carbon dioxide or water vapor. Pressure also changes the strength of circulation. Gas that is too thin cannot transport much energy, while a dense atmosphere can sustain stronger currents and force radiation to travel through a longer path before escaping. The brightness temperature therefore becomes an indirect clue to the thickness of the sky. It does not yet reveal how massive the atmosphere is or identify every molecule within it, but it shows that a major mechanism is preventing the dayside from reaching the state expected for bare rock. Like finding wet ground after the rain has ended, scientists may not see the entire process directly, but they can recognize the effects it has left behind. The temperature difference also changes the picture of the magma ocean. At nearly 2,700 degrees Celsius, much of the dayside would be intensely heated, and the evaporation of rock would be far more rapid. At around 1,800 degrees Celsius, many silicates would still remain molten, but the composition of the vapor above them, the viscosity of the magma, and the extent of the molten region could be significantly different. If the true surface temperature is higher than the brightness temperature because the atmosphere hides it, the ocean below may still be extraordinarily hot, while Webb is primarily observing a cooler layer of gas above it. The measurement does not make this world any less extreme. It simply shows that the heat may be distributed across more layers. Below, there may be glowing magma. Above it, gas absorbs radiation. Higher still, mineral clouds reflect starlight, while winds carry energy toward the dark side. Heat does not remain at the surface, but continually moves through a vast system in which each layer stores or passes along part of it before the energy finally escapes the planet. What makes this especially remarkable is the age of the system. If a thick atmosphere truly exists, it has not only had to endure the intense heat of the present, but also a long history of stellar radiation. Its survival suggests that the planet may contain a larger reservoir of volatile material than expected, or that its interior has been able to replenish the atmosphere for long enough to offset what has been lost. The temperature below the bare rock prediction, therefore, speaks not only to the planet's current weather, but also hints at a complex geological and atmospheric history stretching across billions of years. In astronomy, an unexpected result does not always arrive as a clear image. Sometimes, it appears only as a spectral line lower than predicted, a dip in brightness deeper than expected, or a number that falls outside the place assigned to it by a model. Here, the nearly 900 missing degrees have become the most important part of the signal. That gap carries traces of invisible layers of gas, clouds that have never been photographed, and currents of heat moving beyond the reach of observation. Before a thick atmosphere can be treated as the only explanation, however, simpler possibilities must still be tested. Scientists must ask how efficiently the magma ocean can redistribute heat on its own, whether a highly reflective surface could cool the dayside enough, and how strongly a thin layer of rock vapor might alter the spectrum. By examining each possibility in turn and ruling out those that cannot fully explain the data, researchers can move closer to understanding the sky above this sea of fire. For the moment, imagine removing the thick atmosphere from the picture. What remains is still far from simple. Beneath the stars' fixed light lies an ocean of molten rock, where material continually rises, cools, and sinks again. These convective currents can carry heat away from the hottest region, distribute it across more distant areas, and cause the surface to glow unevenly. If the ocean is deep enough, its internal motion may even connect widely separated regions of the dayside into one vast system, rather than leaving each area to retain only the energy it receives directly. This is the first possibility that must be considered when the dayside temperature appears lower than expected. Perhaps a thick layer of gas is not needed to carry the heat away. The magma itself may perform that role. Hot material near the point that always faces the star could flow toward cooler regions, while colder, denser currents return beneath it. Over time, this circulation would soften the most intense central heat, expand the region of molten rock, and allow energy to radiate from a broader area. This mechanism can certainly occur. A magma ocean is not a motionless lake, and ignoring its movement would make any model too simple. But liquid rock does not behave like water in Earth's oceans. Magma is denser, usually more viscous, and highly sensitive to changes in temperature. As it moves toward regions receiving less starlight, it gradually cools, grows thicker, begins to form crystals, and becomes increasingly difficult to keep in motion. If the night side is covered by a relatively thick solid crust, the dayside ocean cannot flow freely around the entire planet. Hot material may reach the twilight region, but the farther it travels from the light, the more of it solidifies and becomes a barrier to circulation. Heat can still pass through solid rock, but conduction is far slower than the movement of a gaseous layer. The distance from the region of eternal noon to the night side is simply too great for the crust alone to quickly erase the contrast between the two hemispheres. Even within the molten region, convection mainly carries heat upward from deeper layers and from hotter areas toward cooler ones inside the ocean itself. It does not guarantee that enough energy will be transported across the entire horizon. Models that allow strong magma circulation can reduce the temperature at the hottest point, but they still struggle to explain the nearly 900-degree decrease seen in the observations. The sea of rock may help distribute heat, yet it does not appear capable of bringing the dayside to the state recorded by Webb on its own. This limitation does not make the magma ocean any less important. Instead, it suggests that its role may lie elsewhere. The magma helps determine the surface temperature, supplies material to the atmosphere, and stores volatile substances in its deeper layers. It is the source of the system, but it may not be the most efficient pathway for carrying heat around the planet. Between a heavy liquid, confined by regions of solidified rock, and a layer of gas, capable of surrounding the entire world, the atmosphere has a clear advantage when crossing the boundary between day and night. After magma circulation, another possibility appears at the surface itself. Perhaps the planet simply reflects more light than expected. If a large portion of the star's energy is returned to space before being absorbed, the day side would naturally remain cooler. Reflectivity is one of the most important factors in calculations of thermal balance. A dark surface absorbs light efficiently and heats strongly, while a brighter surface retains less energy. The difficulty is that hot magma is generally not a bright mirror. Many kinds of molten rock have relatively dark surfaces, especially when viewed in visible light. They absorb most of the incoming energy and release it again as heat. The exact composition of the ocean could alter its reflectivity, and crystals floating at the surface might create brighter regions. But the surface alone would have difficulty reflecting enough light to explain the full temperature difference. Temporary crust may form in cooler areas. As magma loses heat, the most heat-resistant minerals crystallize first, gathering into thin solid plates that may later crack or be pulled beneath the surface by the material below. If those plates are bright, they could increase the amount of reflected starlight. Near the center of the day side, however, the intense temperature would make such crust difficult to preserve. The surface would be continually remelted, leaving the region receiving the strongest energy, dominated by dark, hot magma. To raise the planet's reflectivity enough across a broad area, a more stable layer of material would need to exist above the surface. Mineral clouds meet this condition better than floating plates of rock. They could spread with the winds, remain suspended at cooler altitudes, and reflect starlight before it reached the magma. But as soon as clouds enter the explanation, the picture is no longer that of a bare, rocky world. It requires a layer of gas thick enough to suspend particles, transport them, and create large regions of condensation. Another explanation lies between these two possibilities. No thick atmosphere, but a thin layer of rock vapor produced directly by the ocean. At temperatures of thousands of degrees, the magma surface does more than glow. It also releases matter. Sodium, potassium, and other more volatile components may leave the liquid first. As temperatures rise further, silicon monoxide, oxygen, and other mineral compounds can also appear in the gas close to the surface. This vapor layer may create its own form of weather. In the hottest region, rock evaporates and enriches the atmosphere with material. Winds carry the vapor toward cooler areas, where its components condense into particles or return to the surface as liquids and solids. Surface flows, or movement within the magma, may then carry the material back toward the hot region, allowing the cycle to begin again. Such a system is sometimes imagined as a rock cycle resembling Earth's water cycle, but operating at vastly higher temperatures. If the only goal were to explain the presence of mineral vapor, the magma ocean would provide a natural source. There would be no need to assume that the planet had retained large amounts of water or carbon dioxide since its formation. The hot surface would create its own atmosphere by evaporating its own material, while gravity held part of that vapor close to the planet. This was once one of the most plausible models for rocky worlds with extremely short orbital periods. The pressure of a rock vapor atmosphere, however, is usually limited by the surface temperature. When the vapor is carried toward colder regions, it condenses quickly and falls, making it difficult for the gaseous layer to remain uniformly thick around the planet. Most of the material would remain concentrated over the day side, especially near the hottest magma. On the night side, where the surface is colder and solid, many components could become trapped on the ground instead of remaining in gaseous form. A thin atmosphere of this kind can still absorb radiation at certain wavelengths, but its ability to transport heat is limited. There is too little material to carry a large amount of energy beyond the horizon, and the gas may condense before traveling far into the dark hemisphere. In a rock vapor model, the dayside must still radiate most of its heat close to where the starlight is absorbed. When the emission spectrum is calculated, the result is generally hotter and shaped differently from the signal web observed. The chemistry of the vapor would also leave its own distinctive signatures. Atoms and molecules originating from rock absorb light at particular wavelengths, producing a spectrum unlike that of an atmosphere rich in water vapor or carbon dioxide. Across the range observed by Webb, a model containing only mineral vapor does not reproduce either the total amount of radiation or the way the signal changes with wavelength especially well. Rock vapor may form part of the sky, but it is unlikely to be the entire sky. This leads to a more layered picture. Close to the surface, rock vapor may still exist and take part in the formation of mineral clouds. Above it, or mixed through it, there may be much larger quantities of volatile substances released from the interior, creating higher pressure and allowing the atmosphere to spread more widely. A thick gaseous layer would not completely replace the rock cycle. It would extend that cycle, allowing matter and heat to travel farther before condensing or returning to the ocean. Simple models are not ruled out by a single measurement alone. Scientists vary each assumption in turn: the depth of the magma, the strength of its circulation, the reflectivity of the surface, the composition of the rock vapor, and the amount of heat transport. Each version produces an emission spectrum and a dayside temperature, which can then be compared with the data. Some models come closer than others, but those without a thick atmosphere repeatedly leave a gap that is difficult to close. This is how an invisible layer of matter gradually becomes necessary. Not because researchers have directly seen the outline of an atmosphere, but because mechanisms without it cannot explain every clue at the same time. Magma currents may transport some heat, but they are limited by regions of solidified rock. The surface may reflect some starlight, but probably not enough without clouds. Rock vapor can form naturally, but it is too thin to carry sufficient energy around the planet. Each possibility still contains part of the truth. The ocean continues to convect. The surface still has its own reflectivity. Rock still evaporates and produces mineral gas. The problem appears only when one process is asked to explain the entire signal by itself. The data seem to belong to a system in which several mechanisms operate together, connected by a layer of gas thicker than the earliest models had allowed. Within that system, the magma sea serves as both a source of heat and a source of matter. Clouds above it alter the amount of starlight reaching the surface. Atmospheric currents carry energy away from the region of eternal noon, while mineral vapor takes part in a cycle of evaporation and condensation. No component exists in isolation, because each one continually changes the conditions experienced by all the others. The cooler than expected dayside, therefore, does not require a single explanation. Heat may be redistributed by the magma, reflected by clouds, absorbed within the atmosphere, and carried toward the night side. Of all these mechanisms, however, only an atmosphere thick enough to surround the planet can connect the entire world, cross regions of solidified rock, and keep energy moving after it leaves the molten surface. As the simpler explanations gradually fall away, the magma ocean does not disappear from the story. Instead, it shifts from being the entire answer to becoming the foundation of a much larger cycle. Above the molten surface, the atmosphere may absorb heat, expand, and begin flowing toward the darkness, carrying with it both energy and the materials newly released from the rock. Above the magma ocean, the atmosphere may be doing what the molten rock below cannot accomplish on its own. It absorbs heat from the surface, expands over the region that always faces the star, and then moves toward cooler areas. No sudden storm or violent eruption is needed to set this process in motion. The lasting temperature difference between the two hemispheres is enough to drive gas away from the hottest region and create currents that circulate around the planet. Earth's atmosphere moves according to a similar principle. Where the surface is heated more strongly, air near the ground absorbs energy, expands, and becomes lighter than its surroundings. As it rises, pressure changes and other air moves in to fill the space it leaves behind. On a small scale, this process can create a coastal breeze. On a larger scale, it helps form weather systems and broad circulation patterns that extend across many latitudes. On a tidally locked world, the source of heat does not move across the sky each day. It remains almost fixed over one hemisphere, while the opposite side is continually deprived of direct starlight. This creates a far more persistent atmospheric engine than the familiar alternation of day and night. The illuminated side continuously supplies energy, the dark side continuously provides a place where gas can cool, and the twilight zone between them acts as a corridor through which heat, matter, and pressure are constantly exchanged. Near the hottest point, gas close to the magma surface absorbs heat and expands. The lower layers may become hot, buoyant, and enriched with substances newly released from the molten rock. As the gas rises, it encounters lower pressure and continues to expand, while also radiating some of its energy into space. At higher altitudes, the flow tends to spread away from the region of eternal noon, moving toward cooler areas and forming a broad branch of circulation across the day side. If the atmosphere is thick enough, this flow does not stop at the horizon. The gas continues across the twilight zone, carrying energy absorbed from the magma sea. The night side is therefore no longer completely isolated from the heat source. It still receives no direct starlight, but it is warmed by air that has crossed half the planet, along with radiation from deeper atmospheric layers and the rock below. As the gas enters the darkness, it gradually cools and becomes denser. Some of it may descend toward the surface, where pressure is higher and heat can be transferred into the colder rock below. The flow may then return toward the illuminated hemisphere through lower atmospheric layers, completing a circulation loop from day to night and back again. The true shape of this motion may be far more complex, but the basic principle remains relatively clear. Hot gas rises and moves outward, while cooler gas sinks and returns toward the waiting source of heat. The planet continues to rotate as the atmosphere moves, even though its rotation is synchronized with its orbit. That rotation means winds do not necessarily travel in straight lines from the hottest point toward the dark side. They may be deflected, stretched into broad bands, or concentrated into powerful currents circling the equator. In some atmospheric models of tidally locked planets, the hottest region is even shifted away from the point directly beneath the star, because winds carry energy onward before the surface, and atmosphere can radiate all of it away. There is not yet a complete thermal map detailed enough to show how strongly such a shift occurs on this world. Webb's current data mainly reveal that the day side emits less heat than a bare surface should. Even without seeing the full wind pattern, however, the missing energy suggests that heat is no longer remaining where it first enters the system. A sufficiently thick atmosphere could carry part of it beyond the horizon, cooling the illuminated side while warming the dark hemisphere. The efficiency of this transport depends first on the mass of the atmosphere. A very thin layer of gas contains too little material to carry much heat. Individual molecules may move rapidly, but the total energy transported remains small because there are not enough particles. As pressure rises, the atmosphere contains more matter above each unit of surface. The gas can absorb more heat from the magma, retain it longer, and carry a significant portion of it elsewhere before the energy escapes into space. Chemical composition also changes the way the system operates. Some molecules strongly absorb infrared radiation, making it difficult for heat from the surface to escape directly. Water vapor and carbon dioxide are familiar examples on Earth, although conditions on a lava planet are vastly different from our own climate. If similar molecules are present in large amounts, they could create a strongly absorbing atmosphere that forces energy through many cycles of emission and reabsorption before it finally leaves the planet. During this process, radiation does not travel along a simple, direct path from the magma into space. An infrared photon emitted by the surface may be absorbed by a gas molecule after traveling only a short distance. That energy causes the molecule to move or vibrate more intensely before being emitted again in a random direction. Some of it continues upward, some returns toward the surface, and some travels sideways through the atmosphere. When the gaseous layer is thick enough, this sequence repeats many times, causing the final escape of energy to occur higher above the surface, where temperatures are lower than in the magma that first produced it. This is why the brightness temperature can be lower than the true surface temperature. Webb may not be seeing the hottest part of the molten sea directly. At wavelengths strongly absorbed by the atmosphere, the telescope receives radiation only from higher layers, where the density is lower and the temperature has fallen. The ocean below may still be hot enough to remain liquid, but the gas above it creates a new emitting surface, cooler and farther from the magma. The atmosphere not only slows the escape of heat, but also changes the direction in which energy moves. Some radiation is sent back toward the ocean, helping keep the surface molten in regions that might otherwise cool more easily. Some travel sideways with the winds, extending high temperatures beyond the center of the dayside. The overall effect may reduce the extreme heat where the starlight is strongest, while preventing the dark side from becoming so cold that every atmospheric component condenses and falls out of the sky. Preventing the atmosphere from collapsing onto the night side is especially important. On a planet whose atmosphere contains many condensable substances, the dark hemisphere can act as a cold trap. If temperatures fall too far, molecules change into liquids or solids and accumulate on the surface, gradually thinning the atmosphere. Strong enough heat transport would keep the night side warmer, limit the amount of material permanently frozen onto the ground, and allow gas to continue circulating around the world. This creates a form of self-sustaining balance. A thick atmosphere transports heat efficiently, keeping the night side from becoming too cold so less gas condenses completely. As long as most of the material remains in the sky, the pressure stays high enough to support strong winds. By contrast, if the atmosphere becomes too thin, little heat reaches the dark side, more material freezes out, and the remaining gas becomes even less capable of transporting energy. The magma below also takes part in this balance. When the atmosphere retains heat more effectively, the molten region may extend farther toward the twilight zone, and perhaps even into part of the night side. A larger ocean creates more contact between liquid rock and gas, allowing more volatile substances to escape upward. This fresh material thickens the atmosphere, further improving heat transport and preventing the molten region from shrinking too quickly. The system does not necessarily continue growing in only one direction. As the atmosphere becomes thicker, pressure at the surface increases, allowing some volatile substances to dissolve back into the magma more efficiently. Changes in temperature also shift the chemical balance between gas and liquid. When part of the atmosphere returns to the molten sea, pressure may fall. When the magma becomes hotter or more vigorously mixed, material may be released again. The sky and the ocean therefore regulate one another through a long sequence of exchanges. In models, winds on planets like this can reach extremely high speeds because the differences in temperature and pressure between the two hemispheres are far greater than those on Earth. Even so, great speed does not necessarily turn the sky into a scene of constant chaos. Over long timescales, these winds may settle into relatively stable structures, much like major ocean currents that maintain a general direction, even though the water within them is always changing. A gas molecule might leave the region of eternal noon, rise upward, travel thousands of kilometers, and cool as it enters the darkness. Along the way, it collides with countless other particles, exchanges energy, and may take part in chemical reactions. If it carries material from the rock vapor, it may even become part of a cloud particle as the temperature falls. That particle may later descend, evaporate again, or be carried into another layer. These circulation patterns transport more than heat. They also carry material from the magma ocean into regions that never come into direct contact with molten rock. Sodium, silicon, oxygen, and volatile substances may be swept across the twilight zone, changing the composition of the atmosphere both horizontally and vertically. The sky above eternal noon, the twilight region, and the night side may therefore differ from one another, even though they all belong to the same atmospheric layer surrounding the planet. On the illuminated side, the intense heat keeps many substances in vapor form. Near the horizon, some begin to condense. Deep within the darkness, mineral particles may grow larger or fall toward the surface. If lower atmospheric currents return toward the dayside, deposited material may be heated again, evaporate, and re-enter the circulation. Part of the atmosphere may then behave like a weather system, while another part serves as a bridge connecting the molten interior with space. The flow of heat across the horizon also makes the boundary between day and night less sharply defined. On a completely bare rocky world, the temperature falls rapidly as the light weakens because there is no layer of matter capable of carrying energy very far. With a thick atmosphere, the transition extends across a much broader region. The surface within the twilight zone receives little direct starlight, yet it is still warmed by the air above and the magma below, allowing the rock to remain soft or molten farther into the darkness. If the magma ocean is truly close to global in extent, the atmosphere may be what allows that state to persist. The star still supplies most of its energy to one hemisphere, but the gaseous layer may distribute that heat widely enough to keep the opposite side from cooling completely. This remains a possibility that depends on atmospheric pressure and composition, as well as the depth of the molten sea, rather than a confirmed picture of the planet. Even so, the current thermal data make a planet-wide connected system seem more plausible than two hemispheres existing in near isolation. Each orbit lasts only a little more than 10 hours, but the atmosphere does not begin again from the start with every new year. Its circulation continues as the world travels around the star, preserving the same hot region, the same cold region, and the same pathways through which energy is transported. Across millions of repeated orbits, the sky has had time to settle into its own steady rhythm, in which the incoming heat, the amount carried toward the night side, and the radiation escaping into space remain close to balance over long periods. That balance does not eliminate variation. Clouds may thicken and then disappear, wind currents may shift position, and the rate at which gas escapes from the magma may change with the movement below. Yet, behind these shorter fluctuations lies a larger structure, sustained by the star's fixed light and the contrast between the two hemispheres. The atmosphere becomes the fastest moving part of the system, continually adjusting to changes unfolding more slowly within the magma ocean. From far away, Webb cannot see individual wind currents. It records only their combined effects. A dayside cooler than bare rock should be, radiation escaping from higher layers, and a spectrum more consistent with a thick atmosphere. Motions that cannot be observed directly still leave traces in the way energy is distributed, much as the flow of water can be recognized from the shape of ripples even when no individual molecule can be followed. The atmosphere, then, is not simply a motionless covering above a sea of fire. It is a network of transport, carrying heat away from the illuminated region, preventing the dark side from cooling too deeply, and moving matter through areas with very different conditions. That motion may explain why the dayside does not release all the heat delivered by the star. But for this gaseous layer to continue performing that work over billions of years, it must have a lasting source of material. While molecules are still gradually lost from the upper atmosphere into space, the ocean below may be quietly supplying new substances to the sky. That replenishment does not need to come from isolated volcanoes, because on a molten world, the entire surface of the sea may become a place where gas escapes from the rock. An atmosphere does not necessarily consist only of material left over from the planet's formation. It can also develop later, layer by layer, as substances once trapped within rock begin to escape toward the surface. On Earth, this process takes place through volcanoes, fractures, and regions of magma deep beneath the crust. On a world where much of the surface may already be molten, the pathway from the interior to the sky is far broader. Instead of a few isolated vents, the entire magma ocean may take part in releasing gas. Rock is often imagined as dry, dense material containing little more than minerals. Yet when magma forms deep within a planet, it can dissolve many different compounds: water, carbon dioxide, sulfur, and other volatile substances may remain within the hot liquid without forming separate bubbles. They begin to separate only when pressure falls, temperature changes, or the composition of the magma no longer allows the same amount to remain dissolved. A bottle of carbonated water offers a familiar image of this process, although the conditions inside magma are very different from those in an ordinary liquid. While the bottle remains sealed, high pressure helps keep carbon dioxide dissolved in the water. When the cap is opened, the pressure above the liquid drops, and gas begins to separate, forming small bubbles that rise toward the surface. In molten rock, the decrease in pressure as material rises can similarly cause volatile substances to leave the magma, forming pockets of gas before joining the atmosphere. On Earth, gas bubbles trapped within thick magma can help produce powerful eruptions. If the gas escapes easily, the magma often flows more gently. If it remains compressed beneath a thick layer of rock, pressure may build before being released. That image should not be transferred directly to a planet with a magma ocean. When the surface is already liquid across a vast area, many substances can escape without forcing their way through solid crust or waiting for a separate eruption. Outgassing may occur continuously across a broad region, without taking the form of isolated columns of fire. The sea of rock then becomes an immense boundary between the interior and the atmosphere. Below, convection carries material from great depths toward the surface. As pressure falls and temperature changes, dissolved compounds begin to separate. They pass through the upper layers of magma, escape into the air, and are carried away from the hottest region by the winds. At the same time, liquid that has lost some of its gas may cool, become denser, and sink again, making room for fresh material rising from below. This process does not need to occur at the same rate everywhere. Near the point receiving the strongest starlight, the surface is hotter and the evaporation of rock is more intense. Closer to the twilight region, temperatures fall, allowing some substances to condense again or dissolve more efficiently into the magma. The depth of the ocean, its mineral composition, and the convective currents below all cause the rate of gas release to vary from place to place. The sky may therefore be supplied by many smaller sources spread across a vast sea of rock, rather than by a single central region. The idea of outgassing usually refers to magma releasing substances already dissolved within it. That is true, but it is not the entire story. At high temperatures, the components of the rock itself can also enter the atmosphere. Sodium and other more volatile elements leave the surface first, while silicon monoxide, oxygen, and additional mineral compounds appear as the magma grows hotter. The gas close to the surface may be a mixture of volatile substances released from the interior and vapor produced by the direct evaporation of rock. These two sources create very different kinds of atmosphere. Pure rock vapor is closely tied to surface temperature. It becomes thicker over hot regions, thins rapidly in colder areas, and readily condenses into mineral particles. Compounds such as water vapor or carbon dioxide can remain gaseous across a wider range of conditions, transport heat more efficiently, and help sustain atmospheric pressure over a much larger area. Webb's current data cannot clearly separate the proportions supplied by each source, but the inferred thick atmosphere is difficult to explain using only the thin mineral vapor immediately above the molten sea. This raises the possibility that the magma ocean contains a larger reservoir of volatile material than early models predicted. The word volatile does not mean that these substances must disappear immediately. It simply describes materials that enter the gaseous state more readily than heat-resistant components of rock. Large quantities may still remain dissolved in magma under high pressure, hidden deep below the surface and protected from stellar radiation. The interior would then serve as a reservoir that the star cannot directly erode. The atmosphere above is still losing material. At high altitudes, molecules are heated, broken apart, or ionized by high-energy radiation. Some gain enough speed to overcome gravity and escape into space. Outgassing from the magma works in the opposite direction, continually supplying new molecules from below. The planet's present state depends on the balance between these two flows, the amount leaving the world and the amount being replaced from its interior. If the magma contains only a small reservoir, the atmosphere will gradually thin. If the supply is large and the release continues steadily, the sky may survive even though atmospheric loss never completely stops. Preserving an atmosphere in this way is not like sealing matter inside a container. It is more like a lake with water flowing out while underground springs continue feeding it. The water level can remain relatively stable for a long time, even as individual portions constantly leave and are replaced. The great age of the star system makes this mechanism especially remarkable. A primordial atmosphere rich in hydrogen would be unlikely to remain intact after roughly 10 billion years in such a close orbit. The atmosphere present today, however, does not need to be the original one. The planet may have lost most of its lighter material early in its history and later formed a secondary atmosphere from substances released by its interior. The molecules now moving through the sky may have spent an immense span of time locked within rock before finally emerging. Earth's atmosphere is also not simply a layer of gas preserved unchanged from the cloud that formed the solar system. Over long periods, geological activity brought water, carbon dioxide, nitrogen, and many other compounds from the interior to the surface. Some returned underground through geological cycles, while other materials were transformed by oceans, rocks, and life. Although the environment of this lava world differs in nearly every respect, the broader principle remains the same. The sky and the interior are not separate systems. The major difference lies in the speed and extent of the exchange. On Earth, the solid crust restricts the pathways available to magma, so gases are released mainly through volcanoes and tectonic boundaries. On a molten world, the contact area between magma and atmosphere may extend across an entire hemisphere. Every region of liquid rock may contribute a small amount, and the enormous total area can turn countless individual releases into a substantial and lasting supply. Heat from the star helps sustain that supply in several ways. It keeps the surface molten, preventing a thick solid crust from sealing off the interior. It increases the evaporation rate of certain components and maintains convection within the upper magma. At the same time, the heat also makes the atmosphere more likely to escape, so the same source of energy both supports the creation of gas and accelerates its loss. The entire system exists within this long-lasting opposition between the star's two effects. A thick atmosphere can also influence the ocean below. As surface pressure rises, the ability of certain substances to dissolve in the magma changes. Gas no longer moves only in one direction, from below into the sky. Some of it may return to the liquid, especially in cooler regions or where pressure is greater. The magma ocean both releases and reabsorbs matter, creating a constantly shifting boundary between what exists as gas and what remains within the molten rock. This exchange depends on the chemistry of each substance. Carbon dioxide, water, and sulfur do not dissolve in magma in the same way. Some are more readily forced out as the magma cools or crystallizes, while others are retained more effectively under high pressure. The composition of the rock also matters. Magma rich in certain minerals may hold water or carbon differently from magma with another composition. Because the exact mixture that makes up the ocean is still unknown, the amount of gas it can store remains a major part of the puzzle. Even the idea of water must be kept far removed from the image of a blue ocean. At the present temperature, liquid water cannot spread across the surface. Compounds containing hydrogen and oxygen may remain dissolved in the magma, exist as vapor in the atmosphere, or be broken apart by radiation in the upper layers. Hydrogen can then escape more easily than oxygen, gradually changing the composition of the gas over time. If water vapor was once abundant, the atmosphere today may retain only part of it or carry chemical traces of a long history of hydrogen loss. Carbon dioxide is heavier and more difficult to remove directly, so it may survive longer if replenished in significant amounts. It also strongly absorbs infrared radiation at certain wavelengths, changing the altitude from which heat can escape. An atmosphere rich in carbon dioxide could therefore be retained more effectively than one dominated by hydrogen, while also helping make the brightness temperature lower than that of the magma surface. This is only one possibility being explored in models, not a composition that Webb has confirmed. Oxygen may also arise through several pathways. It can be produced from rock vapor, released alongside silicon and other elements, or left behind after radiation breaks apart hydrogen-bearing molecules and the hydrogen escapes. The presence of oxygen in such an environment would not imply life. It would simply be part of high-temperature chemistry and the planet's history of atmospheric loss, a reminder that the same molecule can be created by very different processes on different worlds. From a distance, the exchanges between magma and atmosphere cannot be observed directly. Webb cannot see gas bubbles rising, nor has it measured the rate at which material leaves the surface. The current clues come from the planet's heat and emission spectrum, which suggests that the gaseous layer is thicker than a simple rock vapor atmosphere. Magma enters the explanation because it provides the most natural mechanism for sustaining that amount of gas over a long period. This mechanism also changes the meaning of the planet's great age. 10 billion years is not only a span during which the star could remove gas. It is also time for the interior to continue releasing material, for the composition of the sky to evolve, and for the system to reach a new balance after the primordial atmosphere disappeared. A long history does not necessarily lead only to depletion. It may also produce an atmosphere rebuilt many times from reservoirs deep below the surface. The magma sea, then, is not merely a consequence of the planet's close orbit. It may also help the world resist some of that orbit's effects. The same heat that melts the rock opens a pathway for gas to escape upward, while the vast ocean stores material that stellar radiation cannot remove all at once. The sky survives because of a source beneath the surface, and that source is sustained by the very energy once expected to leave the planet completely bare. This opposition does not need to reach a perfect balance. Gas is still escaping, the composition of the magma is still changing, and the internal reservoir is not limitless. Over immense spans of time, the atmosphere may thicken, grow thinner, or shift from one mixture to another. What Webb sees is only one moment in that history, when the present amount of gas is large enough to conceal some of the heat below and transport energy around the planet. Above the ocean, winds carry matter into regions far from the light. Below, convection continues, bringing fresh magma toward the surface. Between these two flows lies a thin boundary, where compounds leave the rock, become gas, and begin circulating through the sky. Some will condense and return to the sea. Some will remain in the atmosphere through many orbits. Others will eventually escape the planet and disperse into space. The sea of rock can therefore be imagined as breathing, though this breath has nothing to do with life and does not occur in clearly separated cycles. It releases matter as magma rises, draws gas back in when conditions change, and maintains this exchange across billions of years. Each molecule crossing the boundary between rock and sky is only a tiny part of the process, but together, countless small movements may create a thick atmosphere surrounding the entire world. The next step is to see this boundary more clearly as a two-way passage. The magma ocean does not only send gas upward, it may also reclaim part of the sky dissolving matter back into itself and acting as a reservoir that regulates the atmosphere's thickness over time. At the boundary between the magma sea and the atmosphere above, matter does not move in only one direction. Some of it leaves the molten rock, enters the atmosphere, and is carried by winds toward more distant regions. Some returns downward, dissolves into the liquid, and becomes part of the ocean once again. The sky is therefore not completely separate from the interior. It is more like a temporary layer of matter suspended between two larger reservoirs: space above, where gas can be lost, and the sea of rock below, where many compounds can still be stored. The idea that magma can absorb gas may at first seem to contradict the image of a hot surface releasing vapor. Yet a liquid can both emit and dissolve gas, depending on its temperature, pressure, and chemical composition at any given moment. Earth's oceans contain carbon dioxide and many other gases from the atmosphere, even as the sea surface continually releases some of them back into the air. Both flows occur at the same time, and the dominant direction changes with the surrounding conditions. Within magma, the exchange is far more complex, but it follows a similar principle. As the pressure above increases, some volatile substances can remain dissolved in greater amounts within the molten rock. When pressure falls, or magma rises closer to the surface, its ability to hold those substances changes, causing matter to separate from the liquid and enter the atmosphere. Temperature also shifts the balance, but not every compound responds in the same way. Water dissolves differently from carbon dioxide. Sulfur depends strongly on the chemical state of the magma, while oxygen can take part directly in reactions with the elements that form rock. There is therefore no fixed boundary where every molecule rising from below remains permanently in the sky. A molecule that has just escaped the molten sea may remain in the atmosphere for many orbits, travel to the night side, and eventually return to the illuminated region. It may also condense into a particle, fall toward the surface, or dissolve back into the magma wherever pressure and temperature allow. Each portion of matter follows its own path, but the combined effect of countless small movements creates a state of balance across the planet. Balance here does not mean that everything stands still. The ocean continues to convect, the atmosphere remains in motion, and the upper layers continue losing matter into space. What may remain relatively stable over long periods is the relationship among these different flows. If the amount of gas released is close to the amount returning to the magma plus the amount escaping the planet, atmospheric pressure can remain near a certain level even as individual molecules within the sky are constantly replaced. A room with an open door can still remain warm if its heater supplies energy at nearly the same rate that heat escapes. The air inside is never truly sealed, yet the average temperature can remain relatively stable. The atmosphere above the magma sea may survive in a similar way. The star removes matter from the upper layers, while the interior supplies fresh material from below, and the ocean reclaims some of the gas whenever pressure, temperature, or composition changes. This ability to reclaim material makes the magma a buffer for the atmosphere. As the gaseous layer grows thicker, surface pressure rises, allowing some matter to dissolve back into the sea of rock and slowing further atmospheric growth. When gas is lost and the pressure falls, compounds within the magma can separate more readily, replacing some of the material that has escaped. This feedback does not guarantee that the sky will survive forever, but it may slow the rate of change dramatically compared with an atmosphere that has. The size of that reservoir depends on the depth of the magma ocean. If the molten layer is only a thin region close to the surface, the amount of material it can dissolve will be limited. If the magma extends to much greater depths, the mass of liquid involved in the exchange increases substantially. In those deeper layers, high pressure may hold volatile compounds within the rock more effectively, protecting them from stellar radiation until convection carries them back toward the surface. This turns the planet's interior into a reservoir of time. Matter may remain within the magma for thousands, millions, or perhaps far longer before being released. The atmosphere observed at any one moment does not necessarily consist of molecules that have only recently left the rock. It may be the result of a prolonged exchange in which some material has traveled between the interior and the sky many times. The crystallization of magma also changes how these substances are distributed. As part of the ocean cools and minerals begin to form, solid crystals often retain volatile compounds less effectively than the surrounding liquid. Water, carbon dioxide, and many other substances are pushed into the remaining magma, making the liquid increasingly rich in dissolved gas. If crystallization continues, their concentration may eventually rise until they are forced out, replenishing the atmosphere even if the entire ocean has not grown any hotter. In the opposite direction, when solid rock melts again, the newly formed liquid may absorb some gas from above the surface. The twilight region and the night side, where temperatures are lower, may experience cycles of solidification and remelting, unlike those in the region of eternal noon. Each area may therefore exchange matter with the atmosphere at a different rhythm, creating a sky that is not uniform in either composition or pressure. Winds connect these regions into a single system. Gas released in the hottest area does not necessarily return to the magma where it first appeared. It may travel across half the planet, gradually cool, and then be absorbed in another region. That material may later move with the magma toward warmer areas before being released once again. On a planetary scale, this could become a cycle in which geology and climate blend together, with molten rocks serving at once as the surface, the ocean, and the reservoir. Not every component participates in this cycle with equal efficiency. Lightweight hydrogen escapes from the upper atmosphere more easily than heavier molecules, so each time matter passes through the sky, the planet may lose a greater share of hydrogen than oxygen or carbon. Over long periods, the chemical balance of both the atmosphere and the magma gradually changes. The present-day sky may therefore differ greatly from the mixture that existed when the planet was young. Even if its total pressure has remained relatively high, changes in composition also affect the atmosphere's ability to retain heat. An atmosphere rich in carbon dioxide absorbs radiation differently from one containing large amounts of water, vapor, or oxygen. As the mixture changes, the altitude from which heat escapes also shifts, altering the surface temperature and the rate of convection within the magma. The ocean changes the sky, and the sky then changes the ocean through the way it stores and redistributes energy. This is a feedback system, not a single mechanism. A thick atmosphere raises the pressure at the surface, helping certain substances dissolve back into the magma. At the same time, it retains heat more effectively, potentially expanding the molten region and increasing the area from which gas can escape. These two effects pull in different directions, and the planet's final state depends on which process is stronger under its particular conditions. Current models can explore different magma depths, volatile inventories, and atmospheric pressures, but they cannot yet identify one unique configuration. Webb has provided strong evidence that heat does not escape as it would from a bare surface, but it has not directly measured how much water, carbon dioxide, or oxygen is dissolved in the sea of rock. The reservoir below is still inferred from the physics of magma and the need to sustain the atmosphere over time, rather than something that has been clearly observed. This caution is especially important when discussing a global magma ocean. If the night side is still covered by a thick solid crust, the liquid involved in this exchange may be concentrated mainly on the day side. If the atmosphere transports heat more efficiently, the magma could extend farther around the planet, exposing a larger part of the reservoir to the sky. Both possibilities allow matter to move in both directions, but the rate and scale of that exchange would differ considerably. No matter how far the ocean extends, the central idea remains the same. The atmosphere may survive longer because most of its material does not remain in the atmosphere at all times. A significant amount may be hidden within the molten rock, where it is not directly exposed to the star's high-energy radiation. Only the portion released into the gaseous layers is easily removed, while the deeper reservoir is supplied gradually by the movement of the interior. This makes the great age of the system less difficult to reconcile with a thick atmosphere. Billions of years is an immense amount of time for gas to escape, but it is also an immense amount of time for magma to release and reabsorb matter through countless cycles. If the original reservoir was large enough, the planet would not need to preserve every molecule from the time of its formation. It would only need to sustain a flow of replacement material long enough to keep the atmosphere from being completely depleted. The atmosphere we see today may be only the visible portion of a much larger store of matter. Above are molecules transporting heat beyond the horizon, forming clouds or gradually escaping into space. Below lies gas dissolved within the magma, invisible from a distance but potentially decisive in determining how much longer the sky can survive. Between them, the surface of the molten sea continually adjusts how much material remains in the air and how much is stored in liquid form. This balance does not need to be perfect in order to matter. The atmosphere may still be thinning very slowly, while the magma gradually loses its volatile components over time. Or a period of stronger convection may release more gas, temporarily thickening the atmosphere before some of it returns to the ocean. Changes like these may unfold over periods longer than the entire history of human observation, leaving Webb to record only an almost motionless cross-section of a process that has been continuing for an immense span of time. The sea of rock, then, does more than breathe gas into the sky. It also retains part of that breath, drawing matter downward and storing it within deeper layers. Each time the atmosphere loses a small portion from its outer edge, the magma reservoir may replace it with a little more material released from within. That balance could help explain why a world heated for billions of years has not yet become a completely bare mass of rock. The star continues to act on the upper atmosphere, and no mechanism can prevent gas loss entirely. The question is not why no molecules ever escape, but why enough remain to obscure part of the magma sea and carry heat around the planet. The answer may lie in a combination of gravity stronger than Earth's, relatively heavy molecules, and an ocean that continually replenishes the portion of the sky that has been lost. In the lower atmosphere, the gas is compressed by its own weight and remains in contact with heat rising from the magma sea. Higher above the surface, the molecules become more widely separated, the density gradually falls, and collisions between particles grow less frequent. This is where the influence of the star becomes most direct. High-energy radiation can break molecules apart, strip electrons from atoms, and transfer enough heat for some of the gas to begin escaping the planet. Viewed only from this outermost region, the atmosphere may seem to be facing an unavoidable process of loss. But atmospheric escape is not like wind blowing away a layer of cloud. The star does not remove the entire sky at once, nor does it affect every molecule in the same way. A gas particle truly escapes only when it gains enough energy and travels in a direction that allows it to overcome gravity. Most of the others continue colliding, changing direction, or being pulled back downward. The erosion therefore takes place at the outer edge, in small amounts at a time, while the denser body of gas below remains held close to the surface. The planet's mass plays an important role in this process. A world roughly twice as massive as Earth, yet not much larger in size, would have substantial surface gravity. Molecules, trying to leave it, must reach greater speeds than they would when escaping from a smaller planet such as Mars. The extreme temperature helps the gas move rapidly, but strong gravity pulls in the opposite direction, making atmospheric escape less efficient than it would be on a low-mass world. This does not turn the atmosphere into a sealed shell. Hydrogen and other light particles can still escape more easily, especially when ultraviolet radiation and X-rays heat the upper layers. When the star was young, this process may have been much more intense than it is today, removing most of an early atmosphere rich in hydrogen and helium. The planet may therefore no longer possess its first sky, but instead retain a heavier secondary atmosphere formed after a long history of loss. Differences in molecular mass make atmospheric escape selective. Lightweight hydrogen reaches high speeds more easily than carbon dioxide, oxygen, or sulfur-bearing compounds. When the upper atmosphere is heated, the lighter components usually leave first, while heavier molecules are retained more effectively. Over billions of years, the atmosphere does not merely grow thinner. Its composition also changes, gradually losing substances that escape easily and becoming richer in heavier material. Even a heavy atmosphere can still lose matter through other pathways. Radiation can ionize molecules. Streams of particles from the star can transfer energy to them, and rapidly escaping light gases may sometimes drag heavier material along. These processes, however, depend on the activity of the star, the structure of the upper atmosphere, and the amount of gas present. There is no reason to expect the rate of atmospheric loss to have remained constant throughout the history of the system. Young stars are generally more active, rotate more rapidly, and release greater amounts of high-energy radiation. Over time, that activity may decline, reducing the pressure placed on the atmosphere today compared with the planet's early history. Most of the primordial hydrogen may have disappeared during the first few 100 million years, but as the remaining atmosphere became heavier and the star gradually calmed, the rate of loss may also have slowed. The sky that survives today did not need to endure the same level of intense radiation for the full 10 billion years. Even the amount of radiation the planet receives does not tell the whole story. What matters is which portion of that energy is absorbed in the upper atmosphere, how hot the gas becomes, and how efficiently it can release heat again. Some components absorb ultraviolet light strongly, while others radiate energy back into space before enough heat can build up. The chemistry of the upper atmosphere, therefore, determines how much of the star's energy is actually converted into escaping gas. A thick atmosphere also contains far more mass than a thin layer of rock vapor. The star may remove matter continuously, but if the original reservoir and the source of replenishment are large enough, the time required to drain the entire atmosphere becomes extremely long. An escape rate that sounds powerful on a human timescale may still remove only a small fraction of the material stored in the atmosphere and magma. It can be imagined as a vast field of sand being slowly carried away by the wind. Individual grains continue to leave, and over time the shape of the landscape will certainly change. But if the layer of sand is deep, the amount lost each day will not make the entire field disappear quickly. If fresh material is also being brought up from below, the surface may persist far longer than the sight of grains blowing away would suggest. On this lava world, the atmosphere may also be supported by the magma ocean below. The previous two sections showed how the sea of rock could release volatile substances and absorb some of them again. This means that the material directly exposed to loss in space is only the portion present in the atmosphere at any given moment. A much larger reservoir may remain dissolved within the magma, protected from stellar radiation and released only gradually as conditions change. The question, then, is no longer whether the star is removing gas. Some material is almost certainly still escaping. What matters is the rate at which gas rises from the interior compared with the rate at which matter leaves the upper atmosphere. If the two flows remain close to balance, the atmosphere can preserve a relatively stable thickness for a long time, even while its individual molecules are continually replaced. That balance may have changed throughout the planet's history. Early on, the star was more active and lighter gases escaped rapidly, allowing loss to exceed replenishment. Later, as the remaining atmosphere became heavier and stellar activity declined, the rate of escape may have slowed. Magma could continue releasing carbon dioxide, water vapor, or other compounds, allowing a secondary atmosphere to form and settle into a more persistent state. Here, persistent does not mean permanent. In the distant future, the volatile reservoir may be depleted, the composition of the magma may change, or the star may continue evolving in ways that alter conditions on the planet. But a state that does not last forever can still endure for billions of years, far longer than the entire span of human history. Webb is observing only one moment within that immense interval, when the atmosphere still appears thick enough to clearly affect the heat escaping from the planet. A magnetic field is sometimes described as a shield that protects an atmosphere, but its role is not simple enough to conclude that a planet with a magnetic field keeps its gas while one without it loses everything. A magnetic field can deflect many charged particles from the star, yet it can also create regions where matter moves along magnetic field lines. It is not yet known whether this world maintains a global magnetic field, so that factor cannot be treated as a certain part of the explanation. What can be said more clearly is that gravity, atmospheric composition, and replenishment from the magma all act in ways that help matter remain for longer. The planet is massive enough to retain large molecules relatively well. After billions of years, its atmosphere may have lost most of its lighter components and become more difficult to remove. Beneath it, the sea of rock may hold a deep reservoir that replaces some of the sky taken away by radiation. Mineral clouds may also influence atmospheric loss indirectly. By reflecting part of the starlight, they reduce the amount of energy reaching deeper atmospheric layers and the surface. They cannot, however, completely block ultraviolet light or X-rays in the upper atmosphere, and their primary role is more likely to lie in the thermal balance below than in directly preventing gas from escaping. They are only one part of a layered system in which each mechanism contributes something to the final state. Among all these processes, the most misleading image may be that of an atmosphere being swept away. The phrase makes the loss seem rapid, direct, and complete. In reality, it is more like a prolonged leak. Lighter molecules leave first, heavier ones remain longer, the composition of the atmosphere evolves, and magma supplies fresh material from below. The star has not removed everything, not because it has stopped acting, but because the planet has not stopped retaining and replacing what has been lost. The survival of this atmosphere also suggests that extremely hot worlds do not all reach the same outcome. Two planets of similar size, receiving similar amounts of starlight, may still develop very different skies, depending on their original volatile inventories, the age of their systems, the composition of their interiors, and the activity history of their stars. One world may become bare rock, while another preserves a thick atmosphere because its magma reservoir is deeper or its gravity slightly stronger. Small differences at the beginning can accumulate into very different results. A planet that retains more gas can transport heat more effectively, expand its molten region, and increase the area from which material is released. A thicker atmosphere also causes heat to escape from cooler, higher layers, changing the way the surface cools. By contrast, a planet that loses its gas early will have a hotter day side, a colder night side, and less ability to sustain a broad exchange between its interior and atmosphere. TOI 561b may belong to the first of these paths, although the current data do not yet reveal exactly how it arrived there. Models must still estimate the rate of atmospheric escape, the amount of matter dissolved in the magma, and the changing activity of the star over time. A thick atmosphere offers a strong explanation for the thermal spectrum, while the mechanism that sustains it is still being reconstructed from many indirect clues. Even so, the original paradox becomes easier to understand. 10 billion years do not necessarily have to leave behind a completely empty world. The lighter gases may have disappeared long ago, while heavier molecules continue to be retained. Stellar activity may have declined with age, gravity may have slowed atmospheric escape, and the magma ocean may have quietly replenished the sky from a deep reservoir. No single mechanism could preserve the atmosphere on its own, but together they may have extended its existence through a large part of galactic history. High above, some molecules are still escaping and will never return. Far below, others have just emerged from the magma and joined the winds circling the planet. Between these two regions lies an atmosphere that is constantly being renewed, continually losing matter, receiving new material, and changing in composition. Its survival does not come from stillness, but from a balance that has not yet been broken. As the gas remains in the atmosphere long enough to travel from the day side toward the night, temperatures gradually fall, and some components begin to change state. Matter that once existed as molten rock may become vapor and then gather into tiny particles in the sky. Above the magma sea, the next stage of the cycle is no longer only wind and atmospheric escape, but the formation of clouds made from minerals. Above the magma ocean, matter does not remain in a single state forever. Material newly released from the surface may begin as hot vapor, blending into rising currents before being carried away from the region receiving the strongest starlight. Close to the sea of rock, temperatures remain high enough for these substances to stay in the atmosphere. But as they move farther from the surface, or drift toward regions receiving less heat from the star, the surrounding conditions gradually change. The gas expands, temperatures fall, and atoms that once moved freely begin to find one another again. This is when part of the sky may become cloud. On Earth, clouds form when water vapor cools and condenses around tiny particles in the air. Water droplets or ice crystals gather in numbers large enough to reflect light, creating the familiar white layers that drift above the ground. The same broad process may occur on a lava planet, but the material involved is no longer water in the ordinary sense. At vastly higher temperatures, the very substances that form rock can rise into the atmosphere, cool, and gather into tiny mineral particles suspended in the sky. Silicates are among the materials that may take part in this process. On Earth, silicates make up most of the rock in the crust and mantle, appearing in sand, basalt, mountains, and many familiar minerals. When the surface becomes hot enough, some of this material can enter the atmosphere as vapor or simpler compounds. As atmospheric currents carry them into cooler regions, condensation begins, transforming matter that once belonged to the magma ocean into tiny particles drifting above the planet. Clouds of this kind would not necessarily look soft and bright like clouds of water. They might form broad layers of fine mineral dust, thin bands of particles that would be difficult to distinguish by eye, or dense, opaque regions stretched by the winds. Their final appearance would depend on the altitude where the particles formed, the speed of the atmospheric currents, the size of the particles, and how long they survived before falling or evaporating again. A sky filled with clouds of rock might therefore consist not of separate shapes, but of a vast mineral veil that turns the light of the star into a dim glow above the sea of fire. Cloud formation begins with a small shift in the balance of heat. As hot gas rises, the surrounding pressure falls and the gas expands. That expansion reduces some of the molecule's kinetic energy, lowering the temperature even before the flow has traveled far from the day side. At higher altitudes, where radiation can escape into space more efficiently, the gas continues to cool. Each substance has its own range of conditions under which it changes from vapor into solid or liquid particles, so different cloud layers may form at different heights. The atmosphere may therefore develop a layered structure. Close to the surface lies a hot, dense region, rich in material newly released from the magma. Higher above, some compounds begin to condense, forming the first cloud layer. Substances that require lower temperatures may continue rising or be carried toward the night side before forming particles. Instead of a single type of cloud surrounding the entire planet, several mineral layers may rest above one another, each interacting with light and heat in its own way. None of these cloud layers has been photographed directly by Webb. The current data show only that the dayside releases less heat than a bare rock model predicts, and mineral clouds are one mechanism that may contribute to that difference. Any picture of their thickness, color, or structure must therefore remain within the realm of models. Even so, the physics of condensation makes the possibility natural. If rock is evaporating in hot regions and the gas is carried into cooler ones, some of that material is unlikely to remain in vapor form forever. Once mineral particles appear, they begin to change the way light moves through the atmosphere. Some starlight strikes the particles and is scattered in many directions. part of it returns to space before ever reaching the magma ocean. If the clouds are bright enough and cover a large area, less energy will reach the surface, leaving the dayside cooler than it would be if the dark rock absorbed all the incoming light. This may account for part of the temperature measured by Webb. The magma ocean below remains extraordinarily hot, but it does not necessarily receive all the energy made available by the planet's close orbit. The cloud layer between the star and the surface acts as a partially opaque veil, returning some of the light before it can travel deeper. This reflection does not need to turn the planet into a brilliant white sphere. Returning even a moderate fraction of the energy to space could significantly change the thermal balance of the entire hemisphere. At the same time, clouds also affect radiation, traveling in the opposite direction. Heat from the magma sea rises as infrared light passes through the atmosphere and searches for a path into space. Depending on their size and composition, mineral particles may absorb or scatter some of that radiation. A cloud layer can therefore reduce the starlight traveling downward, while also slowing the heat moving upward, creating two effects that do not necessarily work in the same direction. If the reflection of starlight dominates, the surface below receives less energy and becomes somewhat cooler. If the clouds are more effective at trapping infrared radiation, the lower atmosphere may remain hot even while the brightness temperature observed from space appears lower. The balance between these two effects determines whether the clouds cool the climate or retain more heat. There is no single answer for every kind of cloud, because small particles, large particles, and different minerals all interact with light in different ways. Even on Earth, clouds do not perform only one function. Low, thick, bright clouds often reflect a large amount of sunlight, helping cool the surface below. High, thin clouds may allow visible light to pass through while trapping some of the infrared radiation rising from the ground. A similar contrast could occur on a lava planet, under far more extreme conditions, with layers of mineral particles taking the place of water droplets and ice crystals. Winds determine where the clouds travel. Particles newly formed in the upper atmosphere may continue drifting away from the region of eternal noon, moving through the twilight zone and into the night side. As the temperature falls further, more mineral vapor can condense, allowing particles to grow or producing thicker cloud layers. The night side may therefore contain more condensed material than the day side, even if the original vapor comes mainly from the magma ocean in the illuminated region. The atmosphere, however, does not move only in one direction from day to night. In lower layers, gas may return toward the hotter region, carrying small particles or material that condensed in the darkness. As it approaches the magma ocean, the temperature rises and the particles begin to evaporate. The minerals return to gaseous form before entering another cycle, making clouds not a permanent covering, but a temporary state within the circulation of rock. A single tiny particle may pass through this transformation many times. It may form in cooler air, drift for thousands of kilometers, descend into a lower layer, and disappear when it encounters heat. Its material then blends back into the atmosphere, is carried elsewhere by the winds, and may condense once more in another region. Through these repeated movements, rock no longer belongs only to the ground. It circulates through the sky in a way that resembles the movement of water among oceans, clouds, and rain on Earth. Despite the resemblance, this cycle operates under profoundly different conditions. Water on our planet changes state within a temperature range compatible with life, while mineral clouds form in an atmosphere hot enough to vaporize many familiar materials. The falling particles bring no coolness, and the surface below is not damp ground, but glowing molten rock. The familiarity lies only in the rhythm of transformation, rising, cooling, condensing, falling, and returning once again. Particle size determines how long the material remains suspended in the atmosphere. Very small particles may be held aloft by atmospheric currents for long periods, drifting around the planet before they descend. As particles collide and combine, they grow heavier, fall more quickly, and become more likely to return to the surface. If the upward currents are strong enough, Even larger particles may remain suspended, creating thick cloud layers in constant motion. Most of this process still lies beyond the reach of direct observation. Webb cannot resolve individual cloud regions, watch them drift across the dayside, or measure the size of their particles. Scientists can only construct hypothetical atmospheres, allow clouds to form under different physical conditions, and calculate how much light each scenario would emit. The models that best match the data help narrow the possibilities, but they do not turn a theoretical picture into a confirmed landscape. Future observations may clarify the role of clouds by tracking the planet's brightness throughout an entire orbit. If bright and dark regions are distributed unevenly, the amount of radiation received will change as different parts of the planet rotate into view. A rough thermal map could reveal where the hottest point lies, how efficiently heat is transported toward the night side, and how extensively clouds may cover the illuminated hemisphere. The composition of the clouds may also leave traces in the spectrum. Each mineral absorbs and scatters radiation in its own characteristic way, although separating those signatures from the signals of the gas and the surface is difficult. As observations cover a broader range of wavelengths and reach greater precision, some possibilities may gradually be ruled out, leaving a clearer picture of the materials suspended above the sea of rock. For now, mineral clouds remain a plausible part of the system suggested by the current data. They connect the ocean with the atmosphere, carry solid matter into the sky, and alter the amount of energy the planet absorbs. They also show that an extremely hot world does not necessarily have a transparent sky. Just above the glowing surface may lie a thick, hazy atmosphere filled with particles that once belonged to the rock below. From a high point within that atmosphere, the magma ocean might not be clearly visible all the way to the horizon. Its light would have to pass through many layers of vapor and mineral particles, becoming softer and more diffuse before blending into the glow of the hot sky itself. In some places, clouds may completely hide the sea below. Elsewhere, thinner openings might reveal a dim orange or white glow, less like flame than light slowly filtering through a dense layer of matter. These clouds do not exist to make the planet gentler. They are simply a natural result of matter moving through regions of different temperatures. Yet by reflecting starlight, trapping radiation, and carrying minerals around the world, they may play a major role in the balance that keeps the dayside cooler than expected. Part of the answer Webb has uncovered may lie not within the magma sea itself, but in the rock that has left the ocean and temporarily become part of the sky. As the particles continue to grow, not all of them can remain suspended forever. Gravity pulls them downward, while atmospheric currents try to keep them aloft. Eventually, some of the material begins to fall through the gaseous layers, creating a kind of rain unlike anything found on Earth. These grains of rock may descend toward the surface, but on a world this hot, not every particle survives long enough to reach the ocean. A tiny mineral particle may begin its existence far above the magma ocean below, within a layer of atmosphere that has cooled enough for matter to no longer remain as vapor. Before that moment, the atoms that formed it were part of molten rock. They escaped from the surface and were carried upward by the wind, moving separately among countless other molecules as they passed beneath the star's fixed light and gradually drifted toward cooler regions. As conditions changed, the atoms came together, bonded around an extremely small seed, and formed the first part of a mineral droplet suspended in the sky. From that moment on, the material begins a different kind of motion. It no longer follows the gas only as separate molecules, because gravity can now act on a particle with greater mass. Atmospheric currents still hold it at a certain altitude, and constant collisions continue pushing it in many directions. But the tendency to fall becomes stronger as the particle gathers more material around it. If many small droplets collide and merge, they grow larger and descend more quickly, until the motion of the atmosphere can no longer keep them suspended within the cloud forever. On Earth, a similar process creates rain. Water droplets form inside clouds, grow, and then fall through the air toward the ground or ocean. On this lava world, the descending material may be made of silicates and other mineral compounds, the very substances that normally form rock. The rain would not carry water from the sky back to the sea. Instead, it would return rock from the atmosphere to an ocean also made of rock, completing a cycle that is vastly different in temperature, yet familiar in the way matter changes state. The path from cloud to surface, however, would not be simple. A mineral particle formed in cooler air would pass through increasingly hot layers as it fell toward the ocean. The denser atmosphere below would increase the number of collisions, while radiation from the magma would transfer more energy into the descending particle itself. If the temperature rose beyond the limits at which the material remained stable, its outer surface would begin to melt, then evaporate and blend back into the atmosphere before the rest could continue downward. Mineral rain, then, would not necessarily reach the sea. Small particles might disappear completely during their descent, leaving their material behind as vapor in the lower atmosphere. Larger particles could survive longer, but they too would have to pass through air that became steadily hotter and denser. The final stage of their fall might be a process of continuous shrinking, as material was stripped from the surface of each particle until no clear boundary remained between it and the surrounding gas. Rain that evaporates before reaching the ground is not entirely unfamiliar in Earth's weather. In regions of dry air, water droplets or ice crystals may fall from clouds and evaporate along the way, forming faint streaks beneath the cloud that never reach the surface. This phenomenon is often called virga. On a lava planet, the broader principle may be similar, although the material involved and the surrounding temperatures would be entirely different. Instead of water evaporating in dry air, silicate droplets might return to vapor as they enter a region too hot for rock to remain condensed. There is no evidence that Webb has directly observed such curtains of rain on TOI 561b. The telescope has so far measured only the heat emitted from the dayside and the shape of a spectrum more consistent with a thick atmosphere. Mineral clouds and evaporating rock rain arise as natural possibilities within models of hot atmospheres, where material from the magma is carried upward and transported through regions of different temperatures. They help construct a physically plausible picture, but they cannot yet be described as confirmed phenomena on this world. If rain does form, its location and appearance would depend strongly on atmospheric circulation. Near the hottest region, temperatures may be too high for many kinds of particles to survive for long, even at high altitudes. As winds carry mineral vapor toward the twilight zone or into the night side, condensation becomes easier. Clouds may thicken there and release material into lower layers, creating a clear difference between the sky above the illuminated hemisphere and the sky beyond the horizon. Some of the rain may reach solid or partially molten rock on the dark side. There, lower temperatures would allow mineral particles to survive longer, settle onto the surface, and accumulate as new layers of material. The composition of this deposit would not necessarily match that of the original magma ocean, because more volatile substances would be transported and condensed differently from minerals that resist higher temperatures. Over time, mineral rain could redistribute material around the planet, removing certain elements from hot regions and depositing them in cooler ones. This process is sometimes described as planetary-scale distillation. In a simple distillation system, more volatile substances leave a mixture first, travel elsewhere, and condense as the temperature falls. On a world divided between permanent day and night, the enormous temperature contrast could perform the same function. The magma sea on the illuminated side would be the region of evaporation. Atmospheric currents would provide the pathway of transport, and cooler regions would become the places where those components condensed and settled. If the cycle continued for long enough, the surfaces of the two hemispheres could gradually develop different chemical compositions. The day side would continually lose more volatile substances from the uppermost magma, while convection from deeper below attempted to replace them with fresh material. The night side would receive additional minerals from the atmosphere, but some of them might remain locked in solid form rather than immediately returning to the hot region. The ocean, atmosphere, and dark crust would then differ not only in temperature, but also exchange elements through a long-running planetary cycle. Deposition on the night side could also change the way the atmosphere is sustained. If too much material became permanently trapped on the cold surface, the sky would gradually lose its condensable components. But the thick atmosphere, carrying heat beyond the horizon, might prevent the dark hemisphere from becoming a perfect cold trap. Transported warmth could cause some deposited material to evaporate again, while lower atmospheric currents might return the vapor toward the dayside. The competition between deposition and renewed evaporation would determine how much material remained trapped in the darkness and how much continued circulating around the planet. In the twilight zone, the cycle may reach a more balanced state. Temperatures could be low enough for particles to form, but not necessarily low enough for all falling material to remain on the surface. A mineral droplet might reach the ground, merge into thicker magma, and then be carried back toward the illuminated region by surface currents. It might instead become trapped within a newly solidified plate of crust, waiting for heat from below to melt that plate once more. The boundary between sky and ground would be continually rewritten there through falling, rising, and melting. If the entire circulation could be observed over a long period, the sky would probably not appear as a fixed cloud layer. Regions of condensation would shift with the winds, altitude, and the amount of vapor supplied by the magma. Clouds could thicken as more material arrived, then gradually thin as particles fell or returned to hotter regions. Rain would appear beneath them, disappear at different heights, and leave behind vapor that continued to drift away. The whole system would resemble a sequence of changing states rather than a landscape with permanent outlines. Light passing through this rain would also be altered. Small particles would scatter starlight and make the sky hazier, while larger ones might obscure the deeper layers below. From space, regions filled with thick mineral clouds and rain could reflect more light, while the amount of infrared radiation escaping would depend on the temperature of the cloud layer. If these particles covered much of the dayside, they could help make the brightness temperature appear lower than the true temperature of the magma surface. Webb does not yet have enough data to separate the effects of clouds, gas, and the surface in each region. Future measurements across different parts of the orbit may reveal how the planet's brightness changes as different areas rotate into view. If the twilight zone or the night side contains more mineral clouds, the variation over the course of an orbit may leave a different signature than it would if the clouds were distributed evenly. Such data would not reveal individual falling particles, but it could offer clues about where condensation occurs most strongly. Different wavelengths also carry information about the size and composition of the particles. Minerals do not absorb every kind of light in the same way, and small particles interact with radiation differently from larger ones. As the observed spectrum expands and becomes more precise, the range of possible cloud models may gradually narrow, revealing which materials best match the signal and which atmospheric layers are most likely to contain them. Until then, rock rain remains part of the science still being inferred, where physics allows such a scene to exist, but observations have not yet come close enough to confirm it. Even though it has not been seen, the mineral rain cycle clarifies something important about the sky above the magma sea. The atmosphere is not merely a place where molecules released from rock are stored. It is part of the planet's geological system, where matter can change from liquid to vapor, from vapor to particles, and then return to the surface. On Earth, geology is usually imagined as something happening deep beneath the ground, while weather belongs to the sky. On a lava planet, those two realms nearly merge, because the clouds and rain are made from the same materials that form the crust. A falling mineral particle does not need to complete its entire descent to take part in the cycle. Even if it evaporates within the atmosphere, it has still carried matter and energy from one altitude to another. Condensation releases heat into the surrounding air, while evaporation absorbs heat again. Countless particles forming and disappearing may help shape the atmosphere's thermal structure, much as the changing states of water profoundly influence weather on Earth. Rain that never reaches the sea can therefore still have a real effect on the sky. It moves matter vertically, changes the opacity of the clouds, and contributes to the redistribution of heat. Some particles return to the magma, some settle in colder regions, while many may continue circulating through repeated cycles of condensation and evaporation. There is no clear endpoint to each cycle, because as soon as matter leaves one state, it begins moving toward the next. Below lies a glowing ocean that may be hidden beneath many layers of gas. Above it are clouds formed from rock, stretched along winds that circle the planet. Between them, particles fall through air that grows steadily hotter, gradually fading and disappearing before they can reach the surface. If such a scene truly exists, it would not resemble a loud, violent rainstorm, but a continuous and almost invisible movement of matter between the sky and the sea of fire. Through this cycle, the boundary between above and below becomes increasingly difficult to define. The ocean sends matter into the atmosphere, the sky forms clouds and returns some of it, and heat from the star keeps the entire process in motion. The final step is to place all of these moving layers within a single landscape, and consider how a thick sky above a magma ocean might appear when light, clouds, and heat blend together. Seen from a distance, this world might not appear as a glowing red sphere of rock suspended in darkness. An atmosphere thick enough to matter would soften the planet's outline, creating a faint luminous layer where hot gas gradually gives way to space. The side facing the star may reflect more light because of suspended mineral particles, while heat from deeper layers escapes at infrared wavelengths invisible to human eyes. Beneath that outer appearance lies the magma ocean, but its hottest regions may be so heavily obscured that their light filters through the sky only as a glow behind many layers of haze. No telescope today can bring us close enough to see the planet's true landscape. Webb has measured the escaping heat and shown that a bare rock model no longer explains the data well, but the color of the sky, the thickness of the clouds, and the shape of the horizon still belong to the realm of inference. Any image must be built from known physical laws: how gases absorb and scatter light, how hot matter emits radiation, the temperatures at which minerals condense, and how far winds may carry them. High in the atmosphere, where the density has fallen and the particles are farther apart, the sky above may gradually darken toward space. Looking down, however, would not immediately reveal a clear surface. Layers of hot gas and mineral clouds below could form a broad region of light, almost like a glow rising from behind a heavy curtain. Depending on the atmospheric composition, some wavelengths may pass through more easily, while others are absorbed and re-emitted many times before finally escaping. Lower down, the atmosphere becomes denser and more opaque. Starlight strikes molecules and cloud particles, scattering in many directions and causing the entire sky to glow rather than remaining concentrated in one sharply defined disk. On Earth, small molecules in the air scatter blue light more strongly, creating the familiar color overhead. In a hot atmosphere containing mineral vapor, carbon dioxide, water vapor, or mixtures that have not yet been identified, the colors would be different. They might lean toward milky white, pale yellow, muted orange, or shades that are difficult to compare directly with our own sky. The true appearance would also depend on the eyes of the imagined observer. Much of the energy emitted by the surface and atmosphere lies outside visible light, so the landscape might appear far dimmer than its temperature suggests. Matter heated to thousands of degrees still glows red, orange, or yellow, but the gas above may absorb much of that light before it reaches higher altitudes. What remains may not be a dazzling sea, but a diffuse radiance in which the light comes from no single point and instead seems to fill the entire atmosphere. The star itself might also look very different from a sharply defined Sunday. In the region of eternal noon, it would remain high in the sky and barely change position, but mineral clouds could blur its edges. If the clouds were thick, The stellar disk might become a white region shining through the atmosphere, like a lamp seen through frosted glass. Where the air was clearer, direct light would be stronger, creating areas of the surface that receive different amounts of heat beneath the same sky. There would be no comforting shade in such an environment. Even where clouds block the direct starlight, the atmosphere and surface would still radiate heat from every direction. An imaginary object placed on the ground would receive energy not only from the star, but also from the hot sky above and the magma sea surrounding it. The difference between an illuminated region and one hidden beneath cloud might be far smaller than it is on Earth, because the atmosphere itself would have become a vast source of radiation, covering the entire scene. Closer to the ocean, the horizon may lose its familiar sharpness. Along an earthly coast, the boundary between water and sky often forms a clear line when the air is transparent. Here, heat haze, mineral clouds, and radiation from the magma may blend together, causing the surface to fade gradually into a luminous mist. The sea of rock would not need to rise in towering waves. It may move heavily through broad convective currents, while cooler regions form dark films that crack apart and sink beneath hotter liquid. The color of the ocean would vary with temperature. The hottest regions might glow yellow or nearly white, while cooler areas shift toward orange, red, and then darker tones as a thin crust begins to form. Viewed through a dense atmosphere, however, those colors would be filtered and blended into a more uniform glow. Only through thinner openings in the clouds, or above especially hot regions of magma, might brighter patches become visible deep beneath the gas. Within this sky, clouds would not necessarily drift gently like white forms on a calm day. The temperature contrast between the illuminated and dark hemispheres could drive powerful currents, stretching clouds into long bands that circle the planet. Mineral particles would continually form, grow, and fall, while others evaporated again after being carried back toward hotter regions. The cloud structure might therefore change constantly, even if the overall circulation pattern remains stable across many orbits. Near the twilight zone, the sky may become thicker and hazier. Starlight must travel through a much longer path in the atmosphere before reaching the surface, causing many wavelengths to be absorbed or scattered. The star would remain low near the horizon, never sinking farther and never climbing higher, creating a lasting state between day and night. Mineral clouds carried away from the hottest region might gather there, where temperatures become more favorable for condensation. The light in this region would not necessarily carry the red tones of an earthly sunset. Its color would depend on the composition of the gas and the size of the particles, perhaps forming a band of pale yellow, dim white, or muted orange along the horizon. Beyond that glow lies the day side and its magma ocean, while in the opposite direction stretches the hemisphere untouched by direct starlight. Between them, winds would continue carrying heat across the boundary, softening the transition far beyond any sharply drawn line. Deeper into the night side, the star disappears, but the sky may not become completely dark. The atmosphere has absorbed heat from the day side and continues to radiate as it moves into the darkness. Most of that energy lies in the infrared, but if the gas and cloud layers remain hot enough, a very faint red glow or dim halo may still linger near the horizon. The surface below could also shine in places where the magma has not fully solidified, or where fractures expose hotter material lying deeper within the planet. The night side may be where mineral clouds grow thicker and falling particles survive for longer. If the surface is cool enough, they may settle into new layers of rock. If atmospheric heat transport remains strong, some of that material may evaporate once again. The landscape would not necessarily be a completely motionless expanse of black stone. It might contain mineral plains built from atmospheric deposits, regions glowing faintly with residual heat, and deep currents carrying material back toward the illuminated side. No sound can be inferred with confidence from the current data, and no real observer could survive in such an environment to hear or see the scene. The pressure, temperature, and atmospheric composition could destroy any instrument not specially designed for those conditions. This picture is therefore not an invitation to stand on the shore of a lava sea, but a way of arranging physical processes into a landscape that can be understood intuitively. What Webb has actually provided is not a color image of this sky. The telescope has shown only that the day side emits less heat than a bare rocky surface should, and that the shape of its spectrum is more consistent with a thick atmosphere. From that evidence, models open the possibility of mineral clouds, heat transport, a magma ocean, and cycles of evaporation and condensation. Every layer in the imagined landscape has a physical foundation, but the extent to which each one is truly present will require further measurements to determine. Future observations may track the planet's brightness throughout its entire orbit, revealing how heat is distributed from the day side to the night. If the hottest region is shifted away from the point directly beneath the star, that would be evidence of winds carrying energy elsewhere. If the brightness changes with wavelength in a particular way, scientists may be able to narrow down the atmospheric composition or the type of cloud particles involved. Gradually, the hypothetical sky may be replaced by a map with fewer uncertainties. Until then, this world remains suspended between data and model. We know that it receives enough heat to melt rock. We know that its day side does not glow like a bare surface. We have strong evidence for a thick atmosphere, but we do not yet know the exact color of the sky, the depth of the magma ocean, or where the clouds are most heavily concentrated. What remains unknown does not weaken the story. It keeps the landscape open, allowing each new measurement to change the way the entire planet appears. A sky above a sea of fire may therefore be far less brilliant and sharply defined than illustrations often suggest. It may be dense, hazy, and filled with layers of matter continually changing state, where starlight is diffused before reaching the surface and the glow of the magma must travel through a long path before escaping. Clouds made from rock drift through hot atmospheric currents, mineral rain falls and vanishes, and the horizon gradually dissolves into the luminous ocean below. The entire scene is sustained by a balance that never stands still. The star continues supplying heat, the ocean continues releasing matter, the atmosphere continues carrying energy across half the planet, and the upper layers continue allowing some gas to escape into space. Over billions of years, that sky may have changed its composition many times without disappearing completely, because beneath it remains an immense reservoir of matter still participating in the cycle. From an extremely faint infrared signal, science has arrived at the possibility of a world where geology becomes weather, rock becomes cloud, and the sky is nourished by a molten ocean. The final meaning of this story does not lie in constructing one more strange scene, but in what that scene reveals. A planet that seemed destined to become bare long ago may still preserve many layers of complexity simply because the matter within it has never stopped exchanging with the space above. When this story began, rock appeared to be the most solid part of a planet, the material beneath every ocean, supporting mountains, and seeming to change only across immense spans of time. On the world orbiting close to the star TOI 561, that familiar state has been almost completely reversed. Rock becomes a glowing liquid. Some of it rises as vapor, while some may condense in the atmosphere and return to the surface. In a place that seemed likely to contain little more than intensely heated matter, Webb has found signs of far more layers in motion. The day side remains hot enough to sustain vast regions of magma, yet it does not emit the amount of heat expected from a completely bare surface. That difference is the most important part of the discovery. It does not produce a clear image of clouds, nor does it reveal exactly what the atmosphere is made of, but it shows that energy from the star does not simply travel down to the surface and immediately escape back into space. A substantial layer of matter appears to stand between those two processes, absorbing heat, distributing it around the planet, and concealing the hottest regions of the molten sea below. This atmosphere may not be the original layer of gas preserved unchanged since the planet formed. Over roughly 10 billion years, many lighter components have probably escaped, especially during the star's younger and more active period. What remains today may have been transformed many times, losing certain molecules while gaining new material from the interior. The fact that the planet still possesses a sky does not necessarily mean the star failed to remove its gas. Material may have always been escaping from the upper atmosphere, while the magma ocean continued replenishing it from below. That exchange makes the original paradox easier to understand. Preserving an atmosphere does not have to resemble keeping matter sealed inside a perfectly closed container. It may be more like a system that is always leaking and always being replenished, where the amount of material in the sky changes gradually without ever being completely exhausted. Magma releases compounds once dissolved within the rock, and under different conditions, some of the gas returns to the liquid. The molecules currently high above the surface may be only the temporary, visible portion of a much larger reservoir extending from the magma sea into the planet's deeper layers. Above that boundary, winds carry heat away from the region that always faces the star. Hot gas expands, crosses the twilight zone, and continues toward the dark side, while cooler currents may return at other altitudes. If mineral clouds form, they reflect part of the starlight before its energy reaches the surface. Rock vapor carried into cooler regions may condense into particles, fall, and then evaporate again as it enters hotter atmospheric layers. Each process explains only part of the picture, but together they create a world capable of functioning as one connected system. Science does not yet know how closely this picture matches the planet in detail. Webb has not directly confirmed silicate rain, photographed bands of mineral cloud, or determined the depth of the magma ocean with certainty. The night side may be covered by a solid crust, or it may retain molten regions if the atmosphere transports enough energy. Water vapor, carbon dioxide, oxygen, and mineral vapor may all contribute to the atmosphere, but their relative proportions remain beyond the reach of current measurements. That incompleteness does not make the discovery less meaningful. What Webb has changed is the simple picture of an extremely hot rocky planet. In the past, the close orbit, great age, and intense radiation seemed to lead toward an understandable conclusion. Given enough time, the world should have been stripped bare, leaving only magma and a thin layer of rock vapor above it. The new data suggests that planetary evolution does not always follow such a straight path. An interior may preserve matter longer than expected. Gravity may make heavier molecules more difficult to remove, and continuous exchange between molten rock and atmosphere may sustain a sky across immense spans of time. The most memorable part, then, is not only the possibility of a magma ocean beneath thick clouds. It is the way every part of the planet connects with the others. Heat from the star melts the rock. Molten rock releases gas. The atmosphere changes the way heat escapes. Clouds may reflect light and return material to the surface. There is no completely fixed boundary between geology and weather, because what forms the ground today may enter the sky, while what drifts through the atmosphere may later return to the sea of rock. This entire cycle may have repeated through countless years, lasting only a little more than 10 hours. During a single day on Earth, the planet completes more than 2 revolutions around its star, yet its evolution unfolds at a much slower pace. Small amounts of gas leave the upper atmosphere, portions of matter are released from the magma, and mineral particles change state. No single movement is large enough to tell the entire story, but across billions of years, together they sustain a condition that the earliest models did not easily predict. From a great distance, Webb receives only a tiny change in light when the planet passes behind its star. In that brief interval, part of the heat disappears from the combined signal, allowing scientists to determine that the day side is cooler than expected. From a change nearly impossible for the eye to notice, the image of an entire sky begins to emerge. Incomplete and still filled with uncertainty, but clear enough to rule out the idea of a completely bare rocky world. Above the magma sea, the atmosphere may still be moving across the horizon. In cooler regions, material that once belonged to rock may gather into clouds and begin to fall. Higher still, Some gas continues escaping the planet's gravity and dispersing into space. Beneath it all, the molten ocean still holds a deep reservoir of matter, quietly returning small amounts to the sky. This world does not preserve its atmosphere through permanence. It keeps its sky through movement, exchange, and a balance that has not yet tipped completely toward loss. Rock has become sea. The sea helps create gas, and the atmosphere in turn helps determine how far the magma ocean can extend. Within the faint infrared light detected by Webb, a planet that seemed destined to contain nothing but fire has revealed something gentler and more complex. Even above an ocean of molten rock, a sky may still endure,